fostering connections and synergies from digital sciences to the private sectors, opportunities in Chile, which will be moderated by our Inria director, Nayat Sanchez-P.
Can you hear me well? Okay? Can you hear me? Yes, no? Give me a sign. Can you hear me now? Okay. Okay, well, thank you. Good afternoon, everyone. Good afternoon, everyone. C'est bon? Hello? C'est bien? C'est bon? Okay. Well, good afternoon, everyone. It is my pleasure to moderate this panel, Fostering Connections and Synergies from Digital Sciences to the Private Sector and Opportunities in Chile. In Inria, we have the mission, as you know, of conducting scientific excellence, research, and also innovation. So this panel integrates a little bit this vision in the program of the Journées Scientifiques Inria Chile, linking these two worlds. We have the honor to count with the presence of distinguished panelists representing diverse industries in France and also in Chile, and with whom we are already collaborating. So I want to call to the stage to Christophe Trillier, responsable d'exploration et nouveaux projets chez Eramet. Christophe. Lloyd L'Espagnol, International Technical Expert, Expertise France, Ministry of Energy of Chile. Álvaro González, Director of the Research and Innovation Center, Viña Concha y Toro. And Mauricio, Senior Project Management Consultant at Michelin. So thank you very much for accepting to take part on this discussion. As you know, we want to strengthen the science and industry linkage, and to dive directly to the topic. What we want to explore with you in this discussion, and with also the audience, is the specific challenges, but also the opportunities that you foresee that lie the intersection with digital sciences and your respective industries, and of course within the private sector and also the academy. Okay. We will have 50 minutes. I will do my best to go with the time. So, and for the panel, I'll go directly to the point. Christophe. Eramet is a mining company, right? which is focused in cobalt, nickel, and some other mines, and more recently in lithium, with the presence in Latin America, in Argentina, and more recently in Chile, right? How do you envision the challenges that you have, approaching a new market as Chile, and how do you think that digital sciences can also help you to foresee and enhance the competitive and also the position of your company and the industry here in Chile?
Okay, thank you, Nayat. I had prepared all my notes in Spanish, but I understood that we will do it in English now, but no problem at all. Yes, so in few words first, so Eramet is a mining company established for more than 125 years in the mining activity, and recently we approached the market of the commodities participating to the energy transition, like you said, nickel, cobalt. Nickel, cobalt, we are mining these metals for a long time, but now it's a different process which will allow us to turn the ore into class 1 nickel salts, which are participating to the battery industry. So we are developing nickel in that sense. We are developing also manganese historically, but the manganese is also participating strongly to the battery market. And recently, when I say recently, 12 years ago, we also jump into the lithium adventure, starting exploration in the overall lithium triangle, counting with Chile, Bolivia, and Argentina. And we decided to start by Argentina, which opened arms a bit wider at that time. So we have now a project in construction in Argentina. It's a plant to produce 24,000 tons of carbonates of lithium per year, starting by next June 2024. And recently, as you may be aware, we have been entering Chile. We have done the acquisition of 120,000 hectares in Chile, in the Copiapó area. And all these, I will say, all these projects are at the final the results of some digital science use. Not only, we are still geologists working hard on the field, but the digital science, the artificial intelligence also help a lot in generating a target for exploration, for example, by and not only in South America, but also in other part of the world where we are exploring. But we are using a lot the analysis of multi-criteria, multi-data, to help us in looking for new projects. As you know, in Chile, where lithium is historically mined, it's almost quite easy to explore, because you just have to go on one salar, white halite, white salt lake, and you are directly on the ground. But we are not only looking for such deposits. We are also exploring for paleosalar, means deposits which are hidden below surface. And for that, we are using a lot of digital science by adding different criteria: geological, geophysical, multispectral analysis, satellite image, and all these data are compiled in one single set of data that the machine is helping us to interpret it and to find the most prospective target, even below 100 meters of quaternary materials like sands, soils. So we are using a lot this type of technology, and it helps a lot, and it works quite well. We are now targeting new exploration target at depth, which without this science we could not have been capable to drill and detect. So the technology is helping us a lot. That's for the exploration. And for the exploitation, for the production, we are also putting sensor everywhere now, even on the pumping wells, where we are capable to detect all the characteristic parameters, physical parameters of the brines that we are pumping, bringing that to one hub, collecting all the data to be able to certify the quality of our brines. We don't have to go to sample directly on site, so it's a gain of time and obviously efficiency, profit. I would say it's like a time proficiency, time profitable to do that. And when we are working with heavy equipment, all the heavy equipments are now also equipped with sensors which are capable to obviously geo-reference these equipment, to know better their position, to optimize the distance in between towards the mine, and also to put sensors on some of the most strategic organs of the machine to detect a future breakdown. So we are doing also, thanks to this science and digital technology, some serious improvement in the way we are managing the fleet of heavy equipment. So yes, technology is everywhere, from exploration to production.
Absolutely, and I imagine that, I mean, with the restriction that you have approaching this new market with respect to the protection of the environment, etc., probably you will have also other constraints in this respect, and also digital sciences could help also to understand what those constraints are, probably.
Yes, yes, absolutely.
Yeah, thank you. And Loic, I will jump to you, because, I mean, you're now the French expert from Expected France, and you're based in the Ministry of Energy, leading also this French-Chilean group on green hydrogen, right? In which, by the way, we as Inria are taking part also. How do you think the green hydrogen market in Chile is? I mean, what is the status of this market? What are the main challenges that you foresee? And how do you think, again, I mean, the same question, how do you think that digital sciences and AI in particular can enhance the competitiveness of French companies or Chilean companies, I mean, in this industry? How do you see the market? What are the challenges? I mean, you are inside the ministry.
Thank you. So I think we're still at the very start of the process, in the sense that there's not mass production neither in Chile or in any other part of the world. Chile, like many other countries, have published a hydrogen strategy back in 2020 with a rather ambitious goal of production. For the colleagues probably in France who are not that familiar with Chile, there's a lot of wind in the south and a lot of sun in the north. So basically this gives a big advantage to Chile in comparison to other countries in the world that do not have these natural advantages. On top of this, Chile wants to produce the cheapest hydrogen in the world, worth, the objective at least is $1.5 per kilo. So this is extremely ambitious. But still, we are at the very beginning, as I was saying, of the process. Many French companies and non-French companies and Chilean companies are developing, or in the stage of developing, projects in the north and in the south. And it takes time. It takes time because basically the technology is not fully there. Off-takers are not ready to buy hydrogen at such an expensive price. You have environmental consideration to be taken into account. So all of these aspects make it quite difficult. But the objective of, I think, the state in general, independently if it's a right or left coalition in Chile, is quite ambitious. There will be challenges, and where probably digital solutions will be will be extremely important. The challenges, or the biggest challenge is the production is far away from the consumption. Basically, we consume mostly here in Santiago area, while the production is hundreds of kilometers, if not thousands of kilometers away from Santiago. So the digital solution will probably help if you want bring in a smart way the energy to the consumption areas, where basically today with gas plant you just turn it off and turn it on, or the other way around, on and off. With green hydrogen made out of renewables, it will be by nature intermittent. So you will need to actually count on technology to bring a bit of intelligence in the system, avoid bottlenecks, because what happens when the sun goes down in the north, while actually the consumption picks up in Santiago, and we're back at home and we start watching TV, et cetera, et cetera. So there's a lot of unknown questions still, I would say, but it's probably a big market opportunity for companies that would have an interest in this specific field of the business.
Yeah, and I imagine that, I mean, it was yesterday, I think, that France announced this priority with respect to the white hydrogen. So let's see how this converges and how this will reflect at the end on the strategy of the green hydrogen or gray hydrogen or whatever. Thank you, Alvaro. I will jump to you. I mean, you are the director of the Innovation Center of the Viña Concha y Toro. Viña Concha y Toro is the biggest, largest producer and exporter of wine in Latin America, right? And probably one of the 10 largest wineries in the world. And you're in Chile. And you are working with innovation, you're working with science, and you're working also with digital science with Inria, right? So, I mean, we have been collaborating in multidisciplinary projects since a while now, and having said that, what do you think are the current challenges of your field, agriculture, I mean, agroecology, and what are the main challenges, and what do you think that the digital sciences can come? I mean, I think it will be easy to answer that.
Thank you, Nayat, for the invitation to this interesting talk, and also to have the opportunity also to show you what we are doing in other industries different from mining, which is the most important sector in Chile, energy, of course. But also we are a producer of wines, forestries, and another important business in Chile. And I think digital transformation, or all the tools that we can have with these digital opportunities are huge and are touching every single step of the value chain. And I think we concentrate in Viña Concha y Toro in some specific aspects where we think we have the most opportunities to add value to what we are doing. In our case, Viña Concha y Toro involved not only in the production of wines, have a huge production of grapes, have a huge production of plants, and also involved on the distribution in different markets. So I think the most important opportunities, of course, agriculture. You have a lot of different variables that play in order to give you the yield of the vineyards, the quality of the grapes that will impact later on the quality of the wines. So I think trying to estimate or forecast this is a huge opportunity for the industry. One of the main challenges today is to forecast yield in our vineyards. Or in other words, trying to know how many kilos I will obtain in a specific vineyard, but 2 or 3 months before the harvest. And also what is happening with the quality of the grape, which is important in any wine country. In France, it's more important because you have a lot of difference in qualities between years. Here in Chile, it's more homogeneous, the quality, but also it's a challenge to try to understand the quality and the moment when you pick up the harvest in order to obtain a good tasting wine. That's from the side from the agriculture. But I will say in the winery also we have a lot of challenges and tools that we can give to the winemakers in order to give them time to do their job, to taste the wines and to blend all the different wines and grapes that they have in order to produce nice tasting wines. And in this case, I think the challenges are in fermentation, and in the case of red wine, we have also a process of extraction, which is we need to model in order to understand how many time it will take this process, and optimize in order to use the investment that we have in our cellars in a better way. Also, to try to build indexes of quality of grapes and wines, I think we have a lot of data. We analyze a lot of variables in the grapes and in the wines. So trying to have a different indexes of quality that can help the winemakers take better decisions also is a good challenge. And finally, I think consumers, it's another important issue for our industry and for any industry that sells goods like wine. And we are building e-commerce in different countries, so e-commerce platforms. So we are beginning to establish B2C models, and we are also obtaining a lot of data from our consumers, and that's another challenge, an opportunity to make more research with them and trying to involve the consumers, not only as they are buying a product, so they are giving back information for take better decisions and to offer better products to them. So we talk a lot about the prosumers. So it's not a consumer, it's someone that is giving back information. So I see here a lot of opportunities also for AI, trying to help us to build the tools for our marketing areas and commercial areas in order to give the better information to this purpose.
Absolutely, I'm very, well, I have nothing else that I agree with you. I mean, we work together, we recently, have a project funded by Corfo, okay, that will be launched in January, so there's a lot, to work on. But before that, I don't know if I told you that we are streaming this live, and we have 4,500 Inria researchers that probably are connected seeing you. So the question to the challenges are also to motivate researchers to understand why Chile and what are the local opportunities here in Chile in the respective industries. Mauricio, I will jump to you. Michelin is specialized in, well, it's manufacture of tires. That's the origin of the business of Michelin. I want to ask you how Michelin is innovating in this business model, in this new era of data, new era of this kind of thing. What are you doing in this respect? Are you innovating this business model to a more probably sophisticated one based on data? What are the challenges of the industry, and how are you approaching that? I will tell now the question in Spanish. Estaba diciendo que Michelin es una empresa que está especializada en la fabricación de neumáticos. Ese es el origen de su core business, right? Y la pregunta viene, digamos, de cómo Michelin está mirando nuevos modelos de negocios alrededor de la incorporación de datos y nuevos procesos dentro de Michelin, más allá de la propia fabricación de sus neumáticos, y cómo esto efectivamente puede ayudar a Michelin a posicionarse en un modelo competitivo y de posicionamiento también acá en Chile.
Bueno, primero que todo, gracias por la invitación. Interesante porque creo que todos, al escuchar Michelin, es sinónimo de neumáticos, ¿sí? Sin embargo, hay un mundo muy amplio, ¿sí? En Michelin. Tenemos 130 años ya de historia en el mundo. Sin embargo, creemos que es muy difícil continuar 130 años más haciendo lo mismo. Por lo tanto, hace bastantes años ya Michelin ha tomado la decisión de diversificar, ¿cierto?, sus líneas de negocios, y entre ellas hoy en día hay una estrategia, podría mencionar, que habla de trabajar en el neumático, dentro del neumático como tal. Después viene trabajar alrededor del neumático, ¿sí?, que tiene que ver con la tecnología y la gestión de flotas, y más allá del neumático, que tiene que ver con la experiencia de nuestros clientes y consumidores, ¿ya? Y ahí es donde entramos, por ejemplo, con la guía Michelin, que todos pueden conocer quizás las estrellas Michelin de los restaurantes, ¿sí? Entonces, y esto abre todo un mundo, ¿ok? Nos proyectamos de aquí al 2030 a que prácticamente un tercio de nuestra facturación provenga desde los servicios. O sea, ya no estamos alineando hacia ese tipo de negocio, ¿sí?, al servicio principalmente, más que la venta de productos. Y también declaramos que somos una empresa enfocada en datos, ¿sí?, y basadas en datos. Es decir, todas nuestras acciones en un futuro se van a tomar, ¿no es cierto?, y nuestras decisiones se van a tomar en base a los datos, ¿sí? Con esto, ¿qué es lo que queremos principalmente? Cuando hablamos de la movilidad sostenible y sustentable, ¿no es cierto?, tenemos una línea de negocio nueva, ¿no es cierto?, que tiene alrededor de 10 años, que se llama Michelin Connected Fleet, que ofrece servicio de gestión de flotas. Esto es a nivel mundial. El grupo adquirió a las empresas más importantes de este rubro, que pasaron a ser parte nuestra, ¿cierto? Y hoy en día podemos decir que en Sudamérica tenemos alrededor de 300.000 vehículos conectados, lo cual nos permite una gran cantidad de datos, de millones de datos, ¿cierto?, que nos permiten tanto a nosotros, ¿cierto?, ofrecer algunos tipos de soluciones, ya sea para los organismos públicos y privados, y además a nuestros clientes, en base a estos insights que tenemos, entregarles, ¿no es cierto?, información para la toma de decisiones. Entonces, a nivel mundial, también tenemos Michelin Connected Fleet, ¿sí?, que está trabajando en lo mismo. Estamos integrando nuestra experiencia de neumáticos con la tecnología, es decir, tenemos tecnología en nuestros neumáticos, por ejemplo, podemos tomar la presión y temperatura de los neumáticos, lo que nos permite también disminuir, ¿no es cierto?, la accidentabilidad, principalmente predecir el fallo de nuestros neumáticos en un 80% aproximadamente, y también, ¿no es cierto?, ayudamos en la disminución de costos de combustible y principalmente también a disminuir la huella de la huella de carbono a nivel mundial. Entonces, tenemos todo un plan y tenemos un sueño, ¿no es cierto?, al 2050, de declararnos como una de las empresas más innovadoras a nivel mundial. Por lo tanto, sí estamos haciendo este cambio de mindset, ¿sí? Queremos hacer cosas nuevas. Estamos en Chile, por ejemplo, ya estamos en construcción de nuestra planta de reciclaje neumático gigante. Es la primera a nivel mundial de Michelin que se está construyendo, que también viene a aportar al país en la ley REP, que tiene que ver con la gestión de residuos, ¿cierto?, de neumáticos. Y también, ¿no es cierto?, estamos innovando en el área de la medicina, ¿sí?, en los veleros, haciendo velas, ¿no es cierto?, para los veleros. Entonces tenemos una gran diversidad de productos, ¿no es cierto?, y esa es la forma en que Michelin espera seguir innovando, ¿no es cierto?, y vivir en el tiempo.
Thank you, Mauricio. I will jump to English just because we have people connected and we have half of the audience that don't speak Spanish. So I just want to take another tour with you with another question. I want to stress a little bit a conversation, with respect to understand, your vision of what is the role of the collaboration between the different stakeholders, right? Because we have different stakeholders here. We have the private sector, we have the academia, we have the universities, the research institutions like Inria and others, and we have the government, right? And everybody has its role. So what do you think that needs to happen, okay, at least in Chile, not in the world, we are not going to solve this problem in the world, but at least in Chile, what do you think needs to happen, right, to connect the industry and the academia and to fill this gap that it's so, the gap is so wide, so far, right? So, Christophe?
Lo puedo hacer en español.
Go ahead. They will miss your answer, but it's
No.
okay, go ahead.
El primer actor para mí es el gobierno. El gobierno siempre, históricamente, tiene datos, muchos datos, en todos los campos. Obviamente voy a hablar de minería, pero cuando se habla de minería, se habla obviamente de comunidades, población, agua, medio ambiente. Hay un montón de información que existe a la fecha que para mí es la primera fuente de información y de datos que hay que procesar. Históricamente estos datos son muy importantes porque a veces también pueden revelar, pueden mostrar crisis a través de los años, secadura, inundaciones, porque la población se fue, porque regresa, un montón de datos que se necesita analizar. Para mí, el gobierno tiene que empujar la comprensión de estos datos y de poner entonces las herramientas necesarias. Para mí, Big Data Analysis para mí es clave para todos los proyectos de desarrollo. Entonces, que el gobierno sea el primer facilitador, pero también el primer interesado, porque no se puede generar un proyecto en el futuro, hablar del futuro sin conocer lo que pasó en el pasado. Obviamente, el gobierno está aquí también para fortalecer la implementación de estas tecnologías a nivel educación en las universidades. La inteligencia artificial es algo que se tendría que enseñar como una materia totalmente a propósito. Entonces, eso también el gobierno tiene que fortalecer para que no sea solo como un proyecto, sino una realidad. Hay países de donde venimos, donde en Europa se empezó a tratar la Big Data desde mucho tiempo. Es muy agradable de trabajar en un país donde efectivamente tiene la data ya procesada. Ayuda muchísimo. Te voy a dar un ejemplo, solo el social. Nosotros cuando trabajamos en un proyecto, uno de los primeros, aquí más para el litio, uno de la problemática la más importante es la de agua. Cuando sabes exactamente qué familia sufrió de una escasez de agua, por qué, cómo, a qué época, generalmente en zonas rurales, campos, es muy importante de poder evaluar rápidamente por qué existe este problema de agua, hacer un mapeo rápido en función de la data para implementar un plan de perforación, un plan de inducción de agua. Entonces, estos datos se tienen que generar fácilmente a través de un sistema digital y no perder un tiempo enorme en eso. Entonces, primer actor, el Estado, y después, obviamente, el segundo es el privado, la empresa privada, que los dos, a través de acuerdos privado-público, se puede hacer maravillosas. Así que para mí, esos son los dos actores que yo pondría en contacto. Y después, como intermediario, las instituciones de investigación, las instituciones como Inria, como las universidades, obviamente como link entre los dos. Y te voy a decir otra cosa y último punto, para mí, al nivel de investigaciones es muy importante porque somos todos en producción casi. Hay el rush de la producción, cada día tienes la cabeza en tus cosas de producción. Eso necesita un poco un tiempo, un espacio un poco, la investigación un poco aparte de eso. Entonces necesitas investigadores que toman el tiempo de realizar los modelos, que toman el tiempo de analizar la data y que toman tiempo de hacer ensayos, simulaciones. Eso toma tiempo, entonces son necesarios, obviamente, son claves porque para implementar digital en nuestro medio de cada día hay que hacer antes estudios y simulaciones y pruebas. Y eso es para mí la única manera de mostrar al gobierno y a los privados que eso sí es factible. Entonces, tres actores, gobierno, privado, y para hacer el lío, el cemento, los investigadores, gracias a instituciones y universidades, por ejemplo.
We'll switch to English just to make participate the audience, and but I think it's very important because I mean there's a role that the private sector should also take. I mean that is fund this research, and I think for example we have the example right now of Concha y Toro that have a research center dedicated to do research and take their time of the research. That I agree completely with you. That is a different time from the production and etc. So it's not only to connect, I mean, to other research institutions, but also to have the ability also to do this research. I mean, the local research inside the companies, right?
Absolutely.
So, what do you think? What is your point? What do you think, Álvaro? What do you think? You're a Chilean, right? So,
yeah.
so you know this. I mean, what happens in Chile very well. I mean, this disconnection between science and industry at the end. What needs to happen to connect these worlds, right? So, what do you think is probably you have like a recipe for doing that.
No,
So, what is your recipe?
I don't have any recipe, but I think in Chile, more and more the people are trying to connect with the research and development and trying to build their own solutions. Okay, because there's two ways of thinking on this from my point of view. The point of innovation, where you can have a developed tool by third party and trying to transfer that technology into your organization. That is a challenge, okay? But also you can do your own research development and building your own solutions. And both activities are, for me, completely different. You need completely different profiles, human capital, to achieve the goals needed for the innovation or for the R&D, okay? I agree completely with you, Christophe, about the stakeholders. I think government, universities and centers, and the corporate are the three main stakeholders in order to build this innovation based on science and technology, so with R&D. But also I will add two stakeholders, maybe which is new for Chile, but it's happening since 10, 20 years, which is the entrepreneurs. So the innovation-driven entrepreneurs and the risk capital agencies also are trying to push innovation in different industries, and I think also we need to put a focus on that more than what we are doing now. For the moment, our center is the focus is on this government, universities and center, and corporate stakeholders trying to collaborate together. Examples are the first, when we begin to think about digital transformation, we begin in 2017 with a huge project from Corfo, government, and we build a project together with the School of Engineering of the Catholic University, trying to build our first platform for the quality of wines. And that's one of our cases of success of innovation, because we have now a platform that we call by now Smart Winery, where we have several AI tools. And now we have the similar strategy with you, with Inria. So we have a Corfo, it's the government, we have the center, which is Inria, and Conchitoro leading a new project with the vision not only to focus on the revolution 4.0, thinking about the 5.0 that we know will be the future of our technology platform for the future.
So it's great, but you say that you need, a vision. You need your vision inside the company, right? You need a funding agency at the end, the government, the vision of the government. But I think, and I don't know if you agree, but we have seen during the last years, I would say, like a change of mindset with respect to the government, with respect to the implication, and trying to connect science and the industry, at least of the challenges, right? The big challenges of Chile, even more. So we see, for example, funding for, lithium or salares or, specific or green hydrogen, this kind of thing. So we're seeing this even more. So probably, this of course, that's the role of the government, but also the private sector should do their thing, right? And take the role if
Yeah. So I think
right?
I agree. Every part of this puzzle is changing. And in the case of companies, I think the most important thing that we are doing is to build, to have the human capital, the researchers inside the company, which are the best way to communicate to the academic researchers also. And trying to build together new projects to the challenges that have the university and also the enterprise. So I think that's it for us is our first learning about how to build relations. You need to be people that talk the
same language. The same language, yeah. And even if they are not the same fields, but the same research language and understand themselves. What do you think, like? You're inside the ministry. Where's your feeling?
I was looking just this morning when preparing for the questions. I was looking at the World Bank statistics because I knew that the R&D expenditure of Chile was quite low in comparison to OECD, but I was quite surprised. It's 0.36%, while the average of OECD is 2.7. So, and more interesting, just to a bit compliment on what both gentlemen were saying, out of the 0.36, 90% of this comes from the public sector, the state, COFO, and only 10% from the private. And if you even deep dive a bit further in, out of these 10%, it's mostly SMEs and pymes, and not the big ones. So obviously coming from France with a French mindset where basically it's about CAC 40 and that's roughly about it. Obviously this is a big change. I haven't been in Chile for a long time, so I as we say in French, I step on eggs when speaking, but I've met with many university people, researchers on many hydrogen projects, and what strikes me is that, so they are presenting their projects, And when I ask, so what's next? Basically, they're saying, we're trying to convince companies to actually step in, but we're still too far away from a market perspective, so they simply do not want to collaborate. So obviously, there's Inria and other centers to help bridge that gap, but this is the reality today. So with hydrogen, there is certainly a lot of opportunity for not only the not only the public sector, the state, as you said, that seems to be quite involved through Corfo and its various ministries, but also maybe through private companies that could indeed develop quite a lot of technologies here in Chile. If you look at what exists today, wind farms, solar panel, et cetera, all of this is imported. Nothing is made here. So there is a risk, and I speak for myself, not representing anyone. There is a risk of duplicating a bit what has happened historically in other sectors, that it will just be extracting something without really creating I would say the value chain in the country. And I think there's an opportunity, but it also depends, just to pick up or to emphasize what Christophe was saying, it's the role, obviously, of the state as the kind of the referee and the private sector.
Absolutely, absolutely. Mauricio, ¿qué crees tú cuál es el papel de la colaboración de las alianzas gobierno, empresa privada, academia? ¿Cuál es el rol de cada uno y cómo en el caso de Michelin tú los ves conectarse? ¿Qué faltaría, ¿no?, en ese espacio de la innovación de Michelin de estos tres actores, ¿no? ¿Cómo lo ven ustedes del sector privado siendo una gran industria? ¿Cómo ven la inversión en I+D y cómo ven conectarse con el resto de los actores para cerrar ese gap?
Mira, la verdad es que cuando escucho colaboración, se me viene a la mente inmediatamente la sinergia, ¿sí? Creo que tenemos que buscar los puntos de encuentro, ¿sí?, entre todos los involucrados, ya sea el sector público y privado y la academia, ¿sí? Y esta es mi opinión personal. Yo creo que muchas veces nos enfocamos en lo que estamos haciendo de manera dedicada, con estrategia, ¿cierto?, con foco. Sin embargo, no miramos mucho a quienes están al lado nuestro y quizás tienen algo que puede hacer sinergia con lo que estamos haciendo nosotros. Entonces, tenemos una mirada un poco sesgada y finalmente creo yo que deberíamos compartir visiones. Es decir, tenemos objetivos como organizaciones, pero además podemos tener una visión compartida, finalmente. No podemos construir, ¿sí? Y ahí es donde tenemos que ver hacia dónde queremos. El otro día, hablando con un niño, que es mi hijo, me hablaba de la astronomía. Se decía, hay tanto por hacer en Chile con respecto a la astronomía, tenemos tanto donde explotar, por ejemplo, la cantidad de datos que nos permitirían quizás hacer tantas cosas. Sin embargo, está todo tan aislado, ¿cierto?, de tan poco conocimiento para el resto, que es difícil colaborar. Entonces, ahí es donde nosotros tenemos que, creo que, cuestionarnos, las personas, tanto como las organizaciones, y ver de qué forma yo contribuyo. En el caso de la compañía, ¿cierto?, de Michelin, está viendo, por ejemplo, acciones que son transversales a nivel mundial, ¿no es cierto?, como contribuir a la disminución de la huella de carbono, por ejemplo. Hoy en día intentamos contribuir, ¿no es cierto?, para la reutilización y el reciclaje de los neumáticos a nivel mundial, que también es algo que impacta en todos lados. Sin embargo, creo que está Michelin y tenemos nuestros competidores, pero nunca se ha pensado hacer algo en conjunto, ¿me entiendes? Cada uno toma una acción por separado y busca su interés. Entonces, creo que ese es el desafío principal.
¿Quién para ti tiene que conectar a estos competidores? ¿Un desafío global?
Yo creo que conectarse con la humanidad, creo que es fundamental. Con el ser, ¿cierto? Volver un poco atrás, porque muchas veces vemos muy hacia adelante, pero no estamos viviendo nuestro presente y no nos acordamos mucho de lo que hemos vivido. Recuerda que el 2020 tuvimos una crisis, ¿no es cierto? Tuvimos la pandemia en Chile y a nivel mundial, ¿cierto? Y hubieron muchas buenas intenciones, hubieron muchas interacciones de personas. Sin embargo, si hoy en día tú le preguntas a alguien, ese sentimiento de ese entonces se ha ido olvidando. Ese sentido de colaboración, de unión, de ayuda, ya se ha ido olvidando y nos ha vuelto a ser individualistas. Entonces creo que por ahí va un poco, a dejar de ser un poco de individualista y vernos como un colectivo, ¿no es cierto? Y ver de qué forma yo puedo contribuir a lo otro, ya sea personalmente y en términos de organización.
We have 4 minutes. What about a final tweet to the audience with respect to probably what do you want, to the audience stay with? What is your final thought with respect to what we have discussed today? With respect to the collaboration, with respect to the challenges, and with respect to how can you, as private sector, fill the gap and to contribute to that 0.36 and to augment that in the future, in the near future. What would you do? Go ahead.
Okay, I will begin. So, just to be very brief, I think the gap that we have there needs what also Mauricio mentioned about collaboration. But I think we need to focus, as you mentioned, Nayat, in a challenge. So this is the way for me to connect, and I think we are trying to build innovation ecosystems in specific locations, because after the pandemic, I think what we really need to understand is the relationship between the other stakeholders need to be face-to-face, to have confidence in the other part and trying to build something. And there's a lot of ways to engage with them, which are accelerators, hackathons, and others. We need to build that kind of methodologies in our specific ecosystems and trying to push that way the main challenges that we have.
Absolutely. Loic, what do you think? What do you think is the role to animate this Franco-Chilean ecosystem, private and public sector?
Yes, I haven't spoken about the Franco-Chilean working group. We're not going to solve the...
But that's the way. That's one way to connect, and that's one way to...
It's probably one modest way. So I of course encourage any companies, research center, professional that have an interest to join this platform. We meet. The objective is to meet about 4 times a year, bringing ministries and bringing companies at the table, as well as research center. Corfo, you've mentioned Inria is here as well, and on a specific agenda, on a specific point, trying to find solutions. So we will not sort out the overall issue, but this is probably just a first step towards increased collaboration, certainly.
Yeah, great. Christophe?
Just adding that we have one common purpose, which is, I don't like the name because it's a bit social responsibility. Let's work on pilot. We are not going to do the jump straight away. It will take years, it will take maybe generation, but piloting small progress on one topic, furthermore for mining, where we have to become credible as actor. I do believe that by doing step-by-step, piloting one topic, water, for example, which is crucial for lithium, let's become more credible using digital science, showing that it's possible to simulate, to see what we could make together, respecting water access for everybody. It's possible to work on that kind of topics. So yes, I agree. We should, as private companies, be able to take one topic, not willing to change everything, but one topic, and showing that working with the government, researchers, universities, were capable to work all together in one direction. Yeah, for me it's a way.
Great. Licio,
One of the
one
solutions.
final tweet? Un tweet final. Colaboración.
Sí.
Colaboración.
Bueno, yo creo, he pensado bastante en esto y creo que hay que trabajar mucho en la brecha digital que tenemos hoy en día. ¿Sí? Muchas veces se nos presentan una gran variedad de sistemas, plataformas, software, ¿sí? Y no le encontramos el sentido. Entonces creo que hay que primero educar mucho, ¿no es cierto?, para que las personas puedan encontrar el sentido de la utilización de la tecnología, de la data, ¿no es cierto?, porque hoy en día muchas organizaciones o personas lo hacen de forma prácticamente obligada, porque tiene que ser, porque la compañía hizo una inversión y se debe utilizar, sin embargo no encuentran un sentido. Entonces, creo que ahí es donde hay que trabajar mucho esa brecha en términos de educación digital y también de enseñar los beneficios de esta tecnología que tenemos hoy en día a la mano de nosotros.
Great, and thank you again, four of you, for having accepted to be here and to connect with the Science and the Academy and to provide us with the challenges in Chile. And we hope that this serve, and you are in the right place because you are connected to the research center. So I mean, we can fill the gap, of course, and that's also our role. So thank you so much again, and thank you.
Undoubtedly, the role of the private sector will be crucial, with constant needs that demand solutions from the sciences. We thank you, Nayat Sanchez-P, and all the participants of this roundtable for such an interesting conversation. Thank you very much. Next, we move on to our second scientific session, Model and Data-Driven Methods, and we invite Antoine Rousseau from the Lemon Project Team Inria Center at University Côte d'Azur, Inria, to chair this session. Please come forward.
Thank you. Hello again. So this is my pleasure to invite Pedro Sa to join the floor. So Pedro received his Master of Engineering Science in Chemical and Bioprocess Engineering in 2012 from this School of Engineering at PUC. He was awarded that year the prizes for Best Master Thesis and Best Postgraduate Student of the department. In 2017, he received his PhD degree in Systems Biology from the University of Queensland under the supervision of Professor Lars Nielsen, right? And in 2018, Pedro joined the Department of Chemical and Bioprocess Engineering at PUC as an assistant professor. And now, since 2021, he took a joint appointment at the Institute of Mathematical and Computational Engineering. So he has been actively involved in the development of novel mathematical frameworks for better understanding biological systems. These frameworks hold a wide range of applications from metabolic engineering to personalized medicine. So the floor is yours. Por favor.
All right. Can you hear me? Yes? All right. Thank you for the kind introduction, and thank you for the organizers for the invitation. Today, I'm going to talk about a little bit of neural networks combined with models, traditional models that have been there for many, many years, and how we can extract information from those models and leverage data-driven learning techniques that could help us develop even better models. So this is a rather fancy name for this talk, advancing the development of complex bioprocesses using neural networks informed by physics. So this is the agenda for my presentation. I'm just going to give you a quick, a brief introduction to what do we understand by biomanufacturing. And then we are going to talk about the main process that drives biomanufacturing, which is fermentation. And then we are going to talk a little bit of the work we have done in our department, our lab, in terms of modeling and control of different processes, and how we are improving those models using data-driven learning techniques based on neural networks. And finally, I'm just going to summarize this presentation and also give you a quick, just a brief explanation of an ongoing, very early project with the industry. This is with Conchitoro. We are actually working on building digital twins for fermentation. I'm just going to give you a little bit of insights of what that is. All right. So yeah, we're going to start with this introduction. So by biomanufacturing, which sounds a little bit fancy, it's not that fancy. It's just the way of referring to the process of manufacturing things, typically chemicals, using cells. So on your right, you can see a typical chemical plant, which involves many different processes, and in some of these processes you have inputs going in and products going out, right? And then you will have sequences, you will have parallel processes, and eventually you will get your product. So this is sort of the same approach we take when we model cells. The main problem is that cells are not very easy to engineer, as opposed to a plant where you have all the blueprints and you know exactly what's going on. In a cell, you don't really know what's going on. Typically, you have some knowledge or some insight, at least a hint of what could be happening, but it's a very much a difficult system to engineer. But in the same way as we engineer and develop these chemical processes, we can also develop these processes in cells. So we can take cells, we can modify them, we can engineer them to make different chemicals that we like, commodity, bio-based petrochemicals, bioplastics, drugs, food, etc. And the idea will be that we engineer these cells so they take raw material, hopefully cheap, sustainable materials, and we produced all the things that we need. That's the dream, at least. So there are many different advantages of using cells as plants for building and producing our stuff. You can see here different advantages. So you can have different products made at high selectivity. When you synthesize things chemically, typically there is only so much you can get due to the different conditions that you require to produce different things. Sometimes you have racemic mixtures, and then immediately drops your yield. Biological systems are also carbon and energy efficient. You don't need high temperatures, high pressures. You can typically ferment at ambient pressure, at ambient temperature, and one at atmosphere pressure, so that's very easy to achieve. It is not the case for chemical processes. You have a lower capital expenditure, which is very important if you try to sell your plant or your project to an investor. A low OPEX, that will be operational expenditure, and also scales. Typically, you require a much lower scale as compared to a chemical process. Overall, that lowers the financial risk. You can also have distributed production as opposed to chemical plants where you have, for example, you need to have all your operation concentrated close typically where the raw material are. In biotechnological processes, you can actually be far away. That is not really a problem, and you can be very distributed because of the scale. So in biotechnological processes, we don't speak of economies of speak of economies of scale, really. We speak of economics of unit number. That is the overall number of plants you have. And also we have an environment that is driven by faster innovation, traditional chemical engineering. I belong to a department of chemical engineering, so I take this very, I'm not trying to trash chemical engineers. I feel like a chemical engineer as well, but there is faster innovation going on in biotechnological processes. So if biotechnological processes are so good and enjoy all these advantages, why is the case that we don't see too many of them? And there are very important disadvantages or limitations that are keeping these processes to actually take off. In many cases they have, but still there is a large room for improvement. So firstly, we have typically low productivities, and we can only achieve very low titers. And that is basically because we are using cells to produce our stuff, and cells have evolved to do other things, and we are now trying to make them do things that we like, and they typically don't like that. And it's just very difficult to make them do what we need them to do. Inhibition and all these kind of things play an important role. And also, the biological plant here is harder to engineer. As I said at the beginning, we are given this plant, and we don't have the blueprints, we don't know what's going on, and we are trying to optimize it. So this is a very difficult problem, and below you can see a graph that is showing how is the capacity for technological processes increasing, especially in the US. So this is something that is going on. It's taking off. There are important companies like Ameris, Genomatica, and Evolva that have taken off, but this is something that requires more work. So at the heart of biotechnological processes lies fermentation, microbial fermentation. And fermentation is basically the process where microbes consume substrates and produce products and grow. So there is one interesting, or among the many different interesting phenomena that happen with biological systems, is something called the metabolic overflow, or in yeast is called Crabtree effect, in humans is called Warburg effect, in bacteria is called metabolic overflow. It's roughly the same thing. Cancer cells actually show this metabolic behavior as well. And it's basically this idea of that we still don't quite understand. There is a lot of information and knowledge that we have gathered, but still we are not quite there. But there is this idea of cells being greedy, and they like glucose. So they often consume more than they can oxidize. And as a result of that, they oxidize glucose, but they also produce CO2 and ethanol in the case of yeast. In the case of human cells, they produce lactate. In the case of bacteria, they produce acetate. So they are greedy, and they do this thing, and we don't know really why. Below, you can see some equations that show the stoichiometries of these different reactions. So if you consume one mole of glucose, fully oxidation you get 38 ATPs. That will be the energy that you get. That is an energetic molecule. And you will get 6 moles of CO2. So if you take the ratio between CO2 and O2, it's 1. So if you are fully oxidizing glucose, that ratio is 1. If you ferment glucose, that is, you don't have oxygen to burn glucose, you produce only 2 ATP and produce a bunch of ethanol. That will be the process that drives wine fermentation and other fermentations. But if you're trying to grow cells, that will be very inefficient. And in the middle of that, when you are growing at high growth rates, that will be the letter mu there, you consume glucose, you consume oxygen, you produce a lot of ATP, but also you produce ethanol. So you are doing both things. You are consuming glucose, producing CO2, but also producing ethanol. And that results in an inefficiency because you will be producing less energy if you consume glucose in that way. So in the plot there, you can see 2 yeasts, the ones that are up there, they say Gram-negative. They don't produce ethanol, so they actually grow quite fast. Ethanol is an important metabolite because at high concentrations inhibits growth. So if you're trying to run a culture and you have ethanol being produced, if you accumulate too much of that, then the cells won't grow any longer. And below you can see other yeasts that are very well known. For example, Saccharomyces cerevisiae, which is the yeast you would use to produce wine or beer. That one produces ethanol at high concentrations, but can grow faster. So even though they run this inefficient metabolism, they can actually grow faster. Very weird phenomenon, and we still don't quite know why. There are some very important hints, though. So, okay, so now we have this phenomenon, and then which is quite important because most of the cells that we use to produce our things, they suffer some kind of overflow metabolism. So then now once you pick your cell, you need to define what is the system you're going to use to culture your cells. So you can choose between, there may be other types of cultures. You can either do it in a batch fermentation or fed batch or a chemostat. That will be a continuous culture. If you are producing wine, you will use a batch fermentation. But the problem of batch fermentation is that even though you can grow fast, there is no control over the growth at which cells grow unless you control the temperature. But you cannot get too high titers, and you cannot also get too high yields. On the other extreme, you have chemostats. The problem is that you can continuously run these processes, but you don't have net growth. And you can achieve high yields, but typically low productivities. And in between, you have a culture that is called fed batch, which is a culture that has an input but no output. And in this culture, you actually concentrate your culture, and you can concentrate your cells. So here you can have an exponential growth where you can control the specific growth rate, you can achieve high productivity and titer. So in principle, this type of systems should solve all our problems. But in reality, this is not really the case. So this is a typical profile of a fed batch culture. I also show in some of the fermenters we have in our lab. So once you start running your culture, you see in green the substrate, and you see how cells are actually eating the substrate, consuming the substrate. You see also that cells need oxygen to consume the substrate, so you can see the blue line also dropping, and you can see in log scale how the cells are growing, which these are in gray. So once you run out of substrate, what you will see is that cells will stop growing. So if you follow the dash line, the different dash lines, you will see that either cells stop growing and then die, and oxygen goes up because there are no longer cells that are actually actively consuming oxygen. Just at that point, when you run out of substrate, then you start feeding fresh media in your culture so cells can actually keep on growing. And when you do that, you see that oxygen, which is the blue line, actually maintains for a while and then drops because cells are accumulating in your culture. The gray line keeps on going upwards, although at a lower rate given by the slope. And also you see that the green line remains very low. That means that your culture is limited in the substrate you pick. So this is known, very well known for many, many years, and using this approach, you can actually culture cells for very high densities, which are required if you want to produce large quantities of your favorite chemical. The thing is, if you look at the literature, there are many different approaches you can take to operate a fed batch culture. It is not very clear which one is the best. Depends on the cells you're using, what is your strategy, what is the control law that you would like to enforce. You can have people trying to control the glucose concentration, or maybe the RQ. RQ is the respiratory quotient that will take what is the amount of CO2 that cells are producing, what is over the amount of oxygen that they are consuming. You can also try to control ethanol production, which is linked to this metabolic overflow. Oxygen, you can also look at oxygen, because if you wanna consume glucose, you need to consume oxygen as well. So if you control the oxygen level, you can actually control growth as well. So for us, it wasn't clear which one is the best strategy, so we try different strategies. So the first step we took was to use different strategies, simulate them, and see which one works best. And that is what we did. We picked 4 different strategies from the literature with some differences and modifications so they can fit within our model. And we tried them. We ran many computational experiments looking at what was the performance of each of them and whether they could be robust in real scenarios. So then you can see in some cases you have to measure one variable and you control the same. Sometimes you have to measure more variables and you can control other variables that sometimes are compounded, like the case of the respiratory quotient. So in order to do this, and we did this computationally, we used a model of metabolic overflow. This is a classical model, very well known, many people have used it. And this model summarizes the metabolism of the yeast in 3 different reactions. One that represents the oxidative glucose consumption. The second is glucose fermentation. When you run out of oxygen, you have to ferment the glucose. There is no other choice. And then the third one is ethanol oxidation. So if you have some oxygen, you can also consume ethanol as well. And basically, the switch between these different types of metabolism depends on an oxidative capacity that we built into the model. So the model has some fixed oxidative capacity, and based on whether you're consuming too much glucose, then the remaining, the overflow, will actually be produced as ethanol. Or if you have enough oxidative capacity and you have ethanol around, you can also consume that. So this is a model that, although is described by ordinary differential equations, has a variable structure. So depending on the state of the system triggers different equations, and then you have this variable structure. And in this case, we also assume that oxygen is typically controlled throughout the fermentation, so we didn't have it as a state of the system. So then we run our simulations, and you can see on your right, you can see the feeding profile that the different strategies produced. And on your right, you can see the biomass concentration, which is the objective that we would like to increase. So all these strategies work on manipulating the feeding rate. That is the rate at which you supply fresh media to the culture, and in that way the cells can grow. So in this case, when you look at all the strategies, you can see that the second strategy, the one that is controlling this RQ coefficient, works the best. And when you look at the robustness, that is, after you have a model, then you can shake the parameters a little bit using Monte Carlo. We can see that also we arrive to very similar biomass concentration, very high biomass concentrations, with a lower variability as compared to the other strategies. So all these results rely on the idea of having a good model, a good simulator of the system. So then we ask, is it actually the case? Is it actually that this is a good or an accurate model of the system? So then when we went into the lab and actually built our own model, starting from models that people have used now more recently. So we took 3 models that have shown very good support in the literature. All of them have variable model structures. They differ in terms of the complexity and the number of parameters. And then we use our own data to calibrate each of them. So we use data on recombinant yeast that produces a carotenoid. That is a molecule that has some color. In this case was beta-carotene. We have in our lab one of the highest accumulators in the world. This is courtesy of Eduardo Agosín in our department. And based on having this culture and this yeast that we would like to optimize the process for producing a lot of biomass, given that the biomass, within the biomass we have this carotenoid compound that has a high value, we would like to maximize the concentration in the culture. So we defined 3 different types of scenario in order to calibrate and identify the parameters of this model. We identify an oxidative regime that will be growing at a moderate, specific growth rate. We identified an oxygen-limited regime where we would operate also at moderate low growth rates, but with very low oxygen available, and also a respiro-fermentative regime that will be growing very fast. That will be the case when cells are taking more glucose than the one they can actually fully oxidize at 2 CO2. We run different in triplicates. We run high cell density fermentations. High cell density fermentations is not difficult to get in the literature. If you look around, you will see probably hundreds of fermentation models, but if you carefully look at what are the conditions of those models or the data they are providing, is typically not high cell density, so this is actually very difficult to achieve and to reproduce accurately. So that was a challenge for Francisco, which was the student working on this project. And we ran a battery of different pre- and post-regression diagnostic tools to assess the fit of each of the models. So the first question we were trying to answer was, which of the models that we know is actually the one that best fits the data in different scenarios, and that should help us to decide and also to then apply our battery of different control strategies to develop the best one. So the first results summarize the oxidative regime results. So in this case, we ran, as I said, different fermentations in triplicate. In blue, you can see the training data, and in green, the test data. So we have tests for all of the conditions we tried. If you look at carefully, it's you can't see the numbers for each of the models, but you will have to believe me. Model 2 is slightly better for ethanol and biomass prediction. Overall, you can see reasonably good fits for all the models. And for each of the models, between 2 and 3 parameters were not identifiable given the data we had. We don't really know if this is a structural issue or rather is a practical issue that we don't have enough data for that. The regions that you observe are the 95% intervals that we predicted using Monte Carlo techniques. Then we have the oxygen-limited regime. Again, in this case, as opposed to the previous one, we don't get good fits for biomass. All of the models, you can see that after 30, 32 hours, they predict higher growth, whereas we see that the culture stops growing, and this was a very interesting thing that we didn't expect. Again, you don't see if you run the fermentation for medium or low densities, but if you go to high densities, then different things or new things start to emerge. In this case, model 3 fits are better and show a lower uncertainty, but still are not fully satisfactory. and between 1 and 2 model parameters are not identifiable for all of the models. They have different, although they have sometimes common parameters, sometimes they also have different parameters, so it's difficult to say which one exactly is the one we cannot identify. And the last one is the respiro-fermentative regime. In this one, cells should be growing the fastest. Here again, we see a problem with biomass feeds. We observe that model 3 is the one that fits better the data, but still lacks some accuracy in terms of the biomass, which is the main variable you would like to predict using these models. And also we have between 2 and 4 parameters that we cannot identify given this data set. Okay, so we were a little bit upset. No, I don't know if upset is the word, but we were a little bit disappointed of all the models because we were expecting to have models that could reproduce and work well up to high cell densities, which was the point of our work. So then we turned our heads and said, okay, what can we do to improve this, the performance? So then we look at something which is now very trendy, I would say. It's called physics-informed machine learning. And the idea is, so you can be in different scenarios, right? So if you are doing computer vision or recognizing different objects, you will have a ton of data. And then you can apply data-driven techniques that can leverage and then exploit all the data you have. On the other hand, if you have not too much data, you will probably resort to typical traditional mechanistic models based on physics. And that works well and has worked well for centuries. But in between, you can have a little bit of both. So you can combine both approaches to produce a model that is hybrid, and there are different ways of you can combine them, right? So this is what we understand in very simplistic terms, physics-informed machine learning. So one of the architectures that has taken a lot of interest lately are PINs, which are physics-informed neural networks. And the idea is that you have your network, provided some architecture, and then in terms of the loss function, you will have different terms. So one of the terms of the loss function will be looking at how well your network fits the data, but other terms are constructed where you can also incorporate a physical model, and you can also ask or constrain your network to also agree with the physical model. So now you have both data, experimental data, observations, and a theoretical model based on physics that can drive and increase the accuracy of your network. And it has been shown in different examples that this approach is quite effective in many cases. Basically, the loss function part related to the model works as a regularizer of your objective function, of your loss function. Another approach for combining traditional models with data-driven or neural networks are hybrid models. And in these models, you actually combine the both of them. There are different ways of combining them, where you can have the neural network feeding into the hybrid model or vice versa. It can be very flexible. And the idea is that within this framework, you can have something that is flexible enough that can explain the data, but also you don't lose interpretability, which was something that lately Pablo was talking about how well we can interpret these actual models. So we went with the second one, and we are looking forward to also try to implement a PIN for our process. So this is the general architecture we tried. So we pick our best phenomenological model, our best physical model, and then in parallel, we feed some of the data we had for our model into a neural ordinary differential equation structure model, and that will feed back into the dynamical model so that we can have an updated version of the state variables. It's a very simple architecture, not a big model as opposed to the models that Dennis was presenting in the morning. Only 2 hidden layers, 15 neurons each, and different activation functions. So we tried this model, and then we've got very nice, interesting results. Firstly, the hybrid model performs better than the best phenomenological model that we had before. Something very interesting happened as well. The model also has lower uncertainty. So when we took the model and shake it a little bit using Monte Carlo simulation, we also saw lower prediction, more tighter prediction intervals for our predictions. We didn't observe overfitting. We ran many different tests to check for that, and the most interesting thing was the reduction in uncertainty. So if you compare the best mechanistic or phenomenological model against our hybrid model, we've got a very interesting increase in prediction. So we improved the prediction in the training data times 3.6, and in the case of the test data, times 1.7. So it was a very nice increase in prediction, and this was consistent across the different conditions, that is, in the different scenarios. So we're testing the model in all the possible scenarios where you can be. Why this works better? This is something that we need to think about a little bit further, but we think it's because of the flexible structure that you can get using neural networks. In the case of phenomenological models, typically you assume fixed parameters, and we know now, and this has been now recently more researched and more studied in the field, that parameters in a cellular culture typically change when you reach high densities. And there are many different phenomena that can take place. We don't really know which of them or which combination could be taking place. There is quantum sensing in the case of cells. There is also the rheology of the culture changes dramatically, so the mass transfer actually changes a lot. That could also play a big role. We don't really know, but what we do know is that if you go to high cell densities, the model that works nice and well in your typical fermentation doesn't work anymore. What did we learn using this model? Well, one of the main messages that or the main conclusions we get is, given that our model predicts well ethanol, and ethanol production is triggered by this idea of growing too fast or too low, we know that this is not related to the critical growth rate or the speed of growth. Rather, we think it's about the yield of growth in terms of when you are at high cellular densities, we think that the yield coefficients actually change, and that's why you see the change or the stop of the plateau of the growth of the cells. There is a very interesting now and active field of research. I would say probably it has been for like 3-4 years, which is called building fermenter files. That is bugs, cells that actually likes fermenters. And so they are building all different genetic capabilities, so they actually like the fermenter, and they can stay there, and you can actually achieve high cell densities. So let me finalize with some short points on what we have done. So if you want to control and optimize a process, you need to first be able to describe, explain, and predict what's going on. That was the work we have been doing so far, and we hope to take now our best model and actually use it to develop even better control strategies to improve the performance of our old processes. We're also looking into the adoption of more interesting and novel architectures like pins. For that, you will need a lot of data, and that's one of the key limitations that has precluded us to using these architectures. And let me just, in 2 slides, give you a sense of what we are doing now. As you may think, wine is something very important for Chile and probably also for France. And so we are looking into adapting and transferring more interesting models or more predictive models for winemaking. Chile is one of the world's largest wine producers. And in the case of white wine, probably some of you enjoy white wine, The fermentation of white wine is very delicate. You have to do it at low temperatures. And that introduces an uncertainty to the process. If you go too low, you want to preserve all the aromas of your wine, then you can run into the risk of having your fermentation stuck. That is that the yeast doesn't consume all the sugar and you don't have wine. But on the other hand, if you go too fast, too hot, you don't control well the temperature, then yeast, you will lose all the aromas, and then you will get a very bad and bland wine. So this is not easy to do, and typically has relied on the expertise of enologists, but sometimes they make mistakes, even though they may not recognize that. So the idea is to have this digital model that is able to predict how the fermentation will behave, what are the outcomes of increasing, lowering the temperature, and also giving recommendations on what to do. So we have this pipeline in progress, working with Conchitoro, which was Alvaro was here just recently, where we are working on combining different types of models. So we have a fermentation model, which is pretty much what you observed before. We are also working with a metabolic model that is able to predict, given some inputs, the production of different aromas during the fermentation. And we are also coupling that to a more physicochemical model of aromas production and equilibrium. So then we can get actually a model that can predict online aromas production. And we'd like to feed that into a neural network. Given that aromas are not very easy to predict, we think we have the intuition that we cannot really predict this using a typical mechanistic model. We need to have something more flexible, and for that, we are thinking on a neural network. And all these things will be packaged and deployed into what's now very trendy digital twins, which is a replica of the physical process. So then wine producers and enologists can play around, predict what's going to happen, and optimize their process. So this is one of the outlook and the futures of this type of techniques that are currently in the pipeline, at least for Conchitoro. We have presented a FONDEF project this year, so we hope, fingers crossed, gets awarded. And with that, I would like to acknowledge and thank my collaborators, Ricardo Perez, my main collaborator at the Department of Chemical Engineering, Francisco Ibanez, who is the PhD candidate. It's about to defend his PhD thesis, and excellent job on the modeling and control of fermentation processes. And also our industrial collaboration with Conchitoro, Ricardo Luna and Cristobal Torrealba. He's doing his PhD in a new program called PhD with Industry, which I think will help to bridge industry and university. And also, lastly, I would like to thank Senia, the RL4, Research Line 4, Physics for Machine Learning, for all the support. Thank you very much.
Thank you. Thank you for this very interesting talk. We have time for a few questions. Yep.
Thank you for your presentation, very good. I have a lot of questions actually, but...
Me too, so keep some time for me.
Yeah.
And on for the break also. Go ahead.
About the hybrid model. Did you take one of these three models that you try, you hybridize, you start from zero? I can imagine that you take a metabolic pathway and you put in the rates probably, I don't know. Can you tell a little bit about more?
Yes, so are you referring to the high cell density fermentation model or to the last part?
The last part with the hybrid
The last
model.
part, right, okay. So, so this is a little bit technical. We can definitely discuss this later,
Yeah.
but so you can have a process model coupled to a metabolic model where you can have your process variables being updated, and based on a current state, you can feed that into a metabolic model that runs a linear optimization program with a given objective function, let's say maximize growth. So by doing that, you can predict the fluxes the yeast physiology at that time point that will update the production of many different things, and then you can feed that into the model for the next time point. So you can actually have it run iteratively for all the time of your simulation. Now, predicting aromas, which is, they are not coupled to growth, they are not primary compounds, it's actually quite hard. And that's why we think we have to build in some type of more flexible model that is capable of capturing that variability and for predicting aromas. I should also say that measuring aromas during fermentation is not easy. So we are actually now working on developing the experimental setup to actually measure the aromas. We cannot really measure the aromas at the end of the fermentation because most of the aromas will be gone. And given that we actually want to optimize for production, we need to be able to measure this online, or not probably online, but inline at least, so we can get a better feedback of what the model is doing. So we are currently working on that. We have experience doing that, not me, but my colleagues in the department. They have built condensers for capturing these aromas and measuring them. So we are pulling a lot of experimental effort and also bringing these new type of models to predict what it's going to be. But yes, this is a very challenging task. We hope it works. We know there is a group in Spain that is doing similar things, not the same, but similar things. So we think we are on the right track, even though we haven't really begun. So, but yes, that is roughly what we are doing. Happy to discuss further later.
Thank you.
Here.
Yep.
Thank you for the presentation. I have a question related about how do you let the neural networks, because you have layers, you have transition functions. So what is the intuition to choose that kind of transition functions, for example? Or just guessing?
No, not guessing. We saw different previous working on that specific activation function and had good results, and we tried with that one. And it worked also well for us. I'm sure there may be other activation functions that give us good or even better results. We didn't do a screen, like a very big screen of different activation functions. To be fully honest, this was the choice of our students, and it worked. So we cannot really complain. Yes, but there may be other choices that are better. Yes.
Thank you.
Thank you. Other questions? Okay, I have one short, and I will have other questions for the break. You mentioned the white wine process and the role of the temperature and the variation of the temperature. So in general, in all the processes you're into, and again, I'm not a specialist of that, but how is time taken into account? I mean, time variation of the system. In particular, for example, the filling rate. Do you accelerate or do you decelerate the rate in the system? Do you increase the temperature up to sometimes to, do you change things during time? Is it controlled or is it constant in time?
Yes, thank you. Yes, so typically the temperature is controlled, and it is not constant. So it's a temperature limited process, actually, wine fermentation. So typically enologists like their wine to start when they think the extraction has happened and they are happy with all the conditions. So before that, they keep the wine temperature low, so there is no fermentation. And what they do then is they actually release the control. So they have a cold control. So once you release the control, then the temperature of the tank will increase. Yeast will actually, between 13 and 14 degrees Celsius, they will actually start fermenting. The temperature will increase, and then the control goes back in, kicks in, and keeps the temperature reasonably constant throughout the fermentation process. So that's the typical recipe for doing white wine, but something that we haven't explored. If you have a model, then maybe there may be a more optimal policy for temperatures. You don't have maybe to have it constant. Maybe you can have it going up or downwards. That is something that we would be looking at once we have these type of models.
Okay. Thank you.
Thank
Well,
you.
thank you again for this very nice talk.
Thank you.
And I think we have a break, right?
Yes, we have a coffee break, 20 minutes in the hall, so enjoy this opportunity for networking, and please come back in 20 more minutes. Thank you very much. We will continue in 20 minutes. For his keynote, I'm sorry, and we came back now with the second part of this session. So Antoine, this is the microphone is yours.
Thank you. And we can start right now. So I think it's Jesus and Michel that are going to, only Jesus, okay. Jesus is from the Centro Inria de Universidad Côte d'Azur, the same as mine actually. And he's in the Epion project team, and he's going to talk about the digital twin at the heart of Inria Epion project team. Please.
Well, thank you very much. First of all, I'll say a small message in Spanish. Gracias a los del comité organizador. Muchas gracias por la invitación. Es un honor y un placer para mí estar aquí. Es la primera vez en Santiago, entonces muchas gracias. Ahora cambio a inglés. I'm going to present to you the work that we do in the Epion team. We are, I think, the largest team at Sofia Antipolis. We are about 40 people. There's 6 permanents and around 35 PhD students and postdocs. In the Epion team, it stands for e-patient and e-medicine. So the idea is to construct a framework of the human, not only on the heart, which is the organ in which I work, but it's just in general. And with the idea is to help clinicians, either to improve the therapy, help with the actual clinical tools to help them to study and maybe learn about anatomy, which is a complicated thing in itself. So we develop a lot of algorithms and computational modeling to help clinicians. That is the core of our research. And I am a member of the computational cardiology team in the team, which is a subteam of Epion. So what we do is we do cardiac modeling, a combination of biophysical modeling with AI and machine learning to improve either the drug testing, therapy decision, training of clinicians, help with the diagnosis, and then also some device design. So in order to do that, or my work, it's on the modeling of the electromechanical activity in the heart. So it's in itself, it's a system that is quite complicated, it's quite complex, because you have an electrical system, a mechanical one, a hemodynamics one that speak to each other. So it's multi-physics and then multi-scales. So it's a quite a big beast to attack. So then one thing is to develop a model from the mathematical point of view and give you solutions. And another one, very different, is to give you a solution that is physiologically meaningful. So for that, we need actual clinical data to calibrate our models. So that's where we get, once we have our computational model, then we need to calibrate it to be able to be used in the clinic. So for that, we use either the ECGs, pressure and volume curves measured usually with the echo, the CT scans or MRIs, and the segmentations that you do once you acquire those images. So now in this particular talk, I'm going to give you like an overview of the projects in which we are involved, which is 4 of them, 2 of them ongoing, and 2 that we're about to start. So I'll start with the first one. It's SIM CardioTest. It's a big European project, which is the consortium. It's private companies, but also public institutions. So it's Inria. From Inria, we have a collaboration between Inria Defrost at Lille, Inria, the Carmen team at Bordeaux, and our in Epion, which is the 3 Inria teams that are involved in this project. We have a collaboration also with the IHU Bordeaux, which is the institution that deals with the electrophysiology modeling of the heart. That they work with the cardiology, the hospital in Bordeaux also. We have a very, very close relationship with them. That's where we usually get our data. So then we have two partners in Spain, one in Valencia, one in Barcelona, another one in Simula in Norway. But we also work with three companies. One is Microport, which develops pacing leads and catheters, which are based in Paris. Another one, which is called ExactCure, which is based in Nice, and they do pharmacokinetics. And then another one, very important one, is a startup in Italy, which is called In Silico Trials. So more on them coming. So then in this project, it deals with the simulation of cardiac devices and drugs for in silico testing and certification. In silico testing and certifications are the key parts in this project, because we want to use computational modeling, and then we want to leverage computational modeling. And then we need to be able to be certified, and that implies quite a lot of things, because what does it, we need to be able to, because we work with companies, the companies usually, they follow certain standards, so we need to be able to, that we stand in those standards. So SIM cardio test comprises three main problems. The first one is the pacing leads and catheters, and inside that main problem, there's a few questions of interest to us, meaning the testing of interventional navigation, so meaning once you do the incision in the actual subclavian vein, how will you be able to reach the lead from the actual vein to the heart? That is one problem. The other one is the quantification of stimulation capture, meaning the lead, how much energy do I need to deliver in the lead to be able to trigger an electrical propagation in the heart. And also, this is very, very hard one to the future, is the prediction of the pacing lead fatigue and tissue fatigue, meaning how long will my lead be usable once I insert it? Because once I put it in, I cannot take it out easily. It's a very invasive procedure. So once you get it in, you better be sure that it works and it will do the things that you said that you were going to do. Then on the second problem is the left atrial appendage occluder. This is a device that is usually used to treat when you have something in the heart, the anatomy of the heart, usually in the left atrial. The left atrium sometimes develops like a little ear that is called the left atrial appendage, which serves to nothing, and it creates problems. So then the clinicians, what they do is usually they just put like a cork that impairs the blood to go into the actual left atrial appendage. So it's the questions that you can usually have from the math point of view is, where do I need to place the lead? So meaning the location in the actual anatomy. And then if you put it in a place where you didn't, what happens to the actual blood and the fluid dynamics around it? So what is the probability of developing thrombi or some sort of thrombosis? And then the third main problem is drug efficacy and toxicity, meaning studying how does the electrophysiology in the heart changes as a function of dosage of certain drugs that are prone to make you more arrhythmogenic or not. So those are the big three problems. And then on the bottom here, we are showing all the software that we use to actually attack these problems. The ones circled in green, they are open source. And then the ones with the orange box, they are commercial software. So the interest of using both is that, of course, once you develop a solver, it will be very difficult for the solver to do everything. So you need to take the best from both worlds and then make it happen. So now, one very key component is concerning to the certification on the actual problem is how right does a computer model need to be in order for it to be useful. So this, usually we have to be sure that what we are developing or our models are credible, and then that they can use it and they will be people who can trust it. So then, exactly as it happens when you have production lines, that they have to follow a certain standard. There's also a certain standard that deals with the validation and verification of computer models. That's the BMV 40 here. The BMV stands for validation and verification. So then, from the research point of view, this can be extremely complicated because you have to come up with a question of interest and then a context of use. And they need to be extremely specific to the problem that you are attacking. So to give you just an idea, on the first main problem, and in the interest of time, I'm only going to speak about the delivery of the energy on the actual lead. That is usually, once it is inserted, I think, can I use the pointer? Yeah. So for instance, the lead has certain configuration. In the specific one that we're using, it's called bradycardia lead. It's just the lead, and at the end has a screw. That one gets attached to the actual tissue. Then in the actual screw, you have some dimensions of a little tip, and it has electrodes at the end. And then you can play, well, they play with the how far apart are they, and then the amount of energy that they can deliver. So then in these kind of leads, one very characteristic that we were interested is this very, very, very specific question is, what are the simulation pulse characteristics? And then we need to say which are the units in which we are measuring, in this case, millivolts, and what is the duration of that actual delivery that I'm going to do. What are those characteristics required for this particular lead in bipolar mode to capture healthy electrical pacing in a cardiac tissue? So you see, just to give you an idea of the amount of detail or how complicated it is, to come up with this specific question, it took about 2 to 3 months. So everybody got together, and then there was the researchers, the R&D part from the lead company. So you see, it's not straightforward, especially from the research point of view, that we are not used to all these standards and verification and validation procedures and guidelines that we need to follow. In those procedures, usually are very long documents that you need to read in advance, and also they are prone to interpretation. So sometimes you read something, you understand one thing, and then the RD guy reads it, and then he understands another thing. So when you pose a question, you don't get usually up to the same ground. So it's quite difficult. But then we are making the effort of being inside those guidelines. So in the context of the how to make it credible, we usually have to do what is called on some models of risk of what you're actually doing. And then in these documents are usually detailed like a somewhat like a division of goes from low, intermediate, and high. How much do you trust your model? But it's just something to keep in mind. And then you need to do the validation and the verification and the validation. The verification means that what you're doing, it's correct. So if you do computer models, you usually write equations. So the first is, you need to be sure that you're solving what you actually say that you were solving. That is a problem in itself. But then when you pass from the equations, for instance, to the actual software, there is also guidelines that you need to follow to be able to say that your software was verified. So it's a lot of different things and guidelines that you need to do, and you need to take into account. And on the sorry. So then that was on the pacing leads. On the second big problem, what does it mean to be able to follow this BMB guideline? So in this, you need to do what you're usually doing computation on fluid dynamics, because it's the left atrial appendage and the blood and then the occluder. Usually, you need to do a series of mesh convergence analysis, meaning take a lot of different resolutions. That's the one that they showed this morning that you need to be, but we usually do the inverse. We just go from a coarse mesh, and we start to decrease or increase our resolution for our case. So that way, we have to compute simulations that are very expensive, but then we need to do it to be able to, to say that our software does what we really need. So then it's quite large what we need to do. We need, as I said, the conversion steps, and also, as I said, the model, it's multi-physics, so you need to do not only one bit of the simulation, so you need to do it for multiple bits, so that takes a lot of time. And then you need to come up with you need to take into account different boundary conditions also on your system, so it's a quite long and dedicated process. And here is just showing you the pipeline. It goes, at the beginning you need to do the image acquisition, you need to do segmentation, then you need to mesh it. Each and every one of those steps, you need special software for it, so you need to be very careful. And then, once you do the meshes, you pass to 3D, and then you can run your simulation. So for instance here, well, it doesn't matter. It's on the validation case on our program. It's from the, okay, cool, thanks. So this is on the validation side. Well, so once, this is a collaboration for the UPF of the Barcelona from the guys with the Institute of Technology and the MIT in the US. So this is just to validate what they did on simulations. So the MIT provided 3D printing. So then they created what Barcelona did on images. They printed, and then they are doing the exact, well, it's a phantom, and they are doing a simulation, and then they are doing also echography on that phantom. So that way, what we computed on simulations, it can be also seen in the actual videos. So it's a very good thing, because it's not, usually you cannot, it's very hard to get the actual data, because you cannot ask for a patient to go into the clinic so they can do something additional to what they already have. So 5. Okay, so this one is just simulations of of the actual fluid dynamics. We can run it at this time. So in the first is just before the implantation and then after the implantation. So you have the occluder, and then we're doing a zoom and seeing what is happening on the actual fluid dynamics inside. Can we go? Doesn't let me pass to the next slide. Okay, the third problem is in the drugs. So we're just basically testing if I don't have a drug concentration, and then I come and then somebody injects like some drug, what is the effect on it on the electrophysiology? So the effects are usually in this slide. We could show videos on the simulations. They're actually on the top is just the men, on the bottom is the female. We're observing that only in the case of for females, when you inject some drug, then that develops proneness to develop cardiac problems. So this here on the bottom right, it's just an arrhythmia that gets triggered only on the presence of that particular drug, and only for women. For men, we're not observing that. So it's a risky thing. Here I'm going to skip in the interest of time. And then after that, the idea is that the in silico trials, the startup will do a platform in which each and every one of those problems will be able to have pre-calculated simulations where people will be able to play with, for instance, all the dimensions of the catheter, the different characteristics, and they will be able to see what will be the outcome of those inputs. So this, okay, next. This we're going to skip in the interest of time. And then the other project that I was going to say is Inner Heart, it's called. It's mainly an
so it was referred to us for VT ablation.
What's happened? And then the idea here is to use what the company InHeart can provide to the clinician to help them do ablations. In here, we usually do a segmentation of the actual patient, and then that patient, thank you. That patient here on the bottom, usually the first thing that they do is they acquire the data. It gets sent to the actual server of the company. The company develops the 3D component or the digital twin in 3D. Then that gets sent to a platform to the clinician. And the clinician, when he's doing the ablation, he can see at the same time the electrophysiology that he maps, but also all the anatomy that this company can provide. So that's a very, very, very nice tool. And there's some part of that model in InHeart which is FDA approved and by the European Commission also. So it's and then some parts of it, like the automatic segmentation, is still ongoing. So the idea is that, as I said, help the clinician as much as possible. So then the other project which we are about to begin, it's called MediTwin. It's a big, big, big collaboration between Dassault Systems and then the majority of the EHUs in France. And the idea for us in Inria and ESU is to study sudden cardiac death. We want to do predictions, especially in the long term, because still to this date, we don't know some of the mechanisms or the causes of this, and they can arrive even to healthy people, which apparently they don't have any problems, but then suddenly they just die. So the idea of this project is to integrate imaging and cardiac modeling, and then again, create a myriad of simulations, because that is the advantage here on the simulations. We can actually perform electrophysiology simulations from places where you usually cannot go in with the catheters. So it's because usually the patient is only on a bed, and then once they insert the catheter, they reconstruct here. What you see on the left is the actual electrical activity on the patient. And then on the right, it's a tool from the company InHeart, where they are replicating the electrical activity that you saw, meaning that here in blue is the catheter, or the position where you just pace. And then you start seeing that it appears like it's this circulatory like motion, which is, this is an arrhythmia. And the idea is identify to which parts of the actual tissue this electrical activity gets clenched. So you see here, it will be the black part here. It's just a place that is dead tissue, so the electricity cannot propagate through there. So it's just, it's very problematic. So the idea is, okay, once you are sure that you can declench an electrical activity on that position of the lead, are you sure that by doing exactly what you did, you're not able, well, the question is, what happens if you do the same pacing, but then from another position? So this is an advantage with computational modeling. You can do simulations from wherever you want, and you will not do anything to the patient, because this is like, it hurts. Every time that they pace, it just hurts. So the idea here is we're doing two simulations again. On the left will be a pacing that they observe on the experiments, and then they just, you do 1, 2, 3, 4, 5 pacings at 500 milliseconds, then you just pace 2 more at 300 milliseconds, then you pace 5 more at 250 milliseconds, and you stop pacing, and then this creates like a weird electrical activity that's on the left. And those are identifying which positions on the actual heart, which by pacing leads you to these kinds of activity, it's of highly importance. On the right, on the video on the right, it's the same pacing protocol, but that we just changed the location on the heart. So once we do that, we do exactly the same thing, but we don't, you're going to see it, it doesn't do these weird activities that it just gets clenched. And it is exactly the same stimulation protocol. So the idea of this project is, okay, once you have created your digital twin, and once you're sure that you trigger this arrhythmia in the actual heart, which points on the actual heart actually trigger this activity? Because those are very important. With that, you can tell the clinician, if you pace from here, you will not, the probability that you generate an arrhythmia is very low, but then if you pace from here, it's very high. So he can concentrate when he's doing the actual mapping to a blade, and he can burn in specific places. So then that's concerning this. And then the last one is just another project that we just started with the Lyon, Marseille, and us. And the idea here is to try to study some, it's called non-ischemic cardiomyopathies. Non-ischemic is because it is not due to infarcts or lack of oxygen, so it's mainly genetic diseases. So this can develop either to a dilated hearts or hypertrophic hearts. So the dilated is just the cavity becomes large, so the walls become small. It loses the ability to pump, so that creates problem. The other side, the cavity becomes smaller, so there's less volume, and the wall becomes large. But it's very strange because even though it doesn't change or it doesn't lose the ability to pump, it creates also problems because now the cavity is very small. So we're trying to study and see what's going on. So the idea is we want to do long-term predictions. We need to integrate multi-scale data. That's quite hard. And the idea is to combine it with AI. And this is with again, in the same philosophy of our team, is just to help the clinician with whatever we can. So that's it. Thank you very much.
Thank you. We have time for one question. Yep. Mike? No Mike? Okay.
Thank you for the talk. Just two very short questions. The first one, you showed an image of female and male hearts, and one of them was being affected by a drug. Is that because of the anatomy that is different, or is it physiological difference? And the second question, so I give the mic away. You mentioned also in one part that you were going to develop 3D hearts. So why would you do that and not only use the digital twin? Is it because of the physicians like to have a physical model of the heart? Thank you.
Okay, the first question first. It was two geometries. The geometries were the same. We only changed the fact that we were introducing a drug to the female. That was it. So that was extremely very unexpected, but also very alarming at the same time. So it's because that means that the clinicians, they need to take into account that immediately. So that's the first. And then the second one, the creation of the 3D hearts, we don't need it, but as we want to, especially in the SIM CardioTest project, we want to be able to follow these verification and validation guidelines. So we need those, anything that we can have additional to what we already observe, it's a plus to validate our models. So that is the interest. It's like the validation.
Thank you. Thank you very much. And now I'm pleased to welcome Paula Aguirre. Paula is assistant professor here at PUC in the Mathematical Institute, and she's also associated to CENIA and to CIGIDEN, ¿verdad? Sí. Paula, the floor is yours.
Thank you, Antoine. How do I? Okay, thank you very much for the invitation today and for everyone who has stayed all through the afternoon. So, as Antoine mentioned, I'm a professor at the Institute for Mathematical and Computational Engineering here at Católica, and I've been a researcher for a while at CIGIDEN. This is the Research Center for Integrated Disaster Risk Management, and recently I've also come to work at CENIA, doing research in different topics related to artificial intelligence. And of course, being in these two great centers, my goal is to merge as much as possible these two worlds. And on one hand, try to use and apply artificial intelligence to bolster and advance our research on disaster science. And at the same time, use that experience to learn more about the applications and the developments of artificial intelligence that can illuminate our knowledge on this area. So one of the areas where these topics are currently merging is in the analysis of risk and resilience of complex systems, okay? So at CIGIDEN, we've been working for a while at trying to understand the impacts of different hazards, like earthquakes, tsunami, floods, and wildfires, on complex systems like, for example, urban environments, or also critical infrastructure that is key to the recovery and to the resilience and to the sort of the impact that these events may have on the physical environment, but most importantly on communities and society as a whole. So if we look only at the case of earthquakes, what happens is that in large earthquake scenarios, the overall impact is critically determined by the behavior and the performance of networks like water, electricity, transportation, and of course, healthcare facilities, okay? So people are facing maybe the loss of their homes, the lack of critical utilities like water and electricity, and at the same time they may suffer injuries that require emergency medical attention. And on the other hand, hospitals at the same time, and the whole healthcare network is also suffering from the lack of electricity and problems with transportation and with, for example, traffic of ambulances, etc. So it's a very complex, interdependent problem with a lot of cascading effects. And we've been slowly trying to sort of address and tackle this problem from many different perspectives. So just to give you an example, for example, we've been working in the last years at this integrated problem of critical networks in the regions of Valparaiso and Santiago, where if you can see easily on a map, we have these three networks, transportation, electricity, and healthcare, that are geographically completely overlapping and also functionally depending on each other. And it's a critical area because these are regions that englobe roughly 40% of the Chilean population. Okay, so any impact in terms of cascading effects of these networks has a very significant impact on the Chilean society. So the sort of the overarching questions behind this research is how we can actually compute earthquake vulnerability, risk, and resilience in a specific geographic setting, just to make it a little more concrete. And also how, as a second question, how we can estimate the propagations of uncertainties in this risk and resilience metrics within a given network, across networks, and also across regions. Okay, so to sort of set out the problem, if we look at resilience, well, we first need to sort of start with a definition. Okay, so we understand resilience as the capacities of a system, a person, or a community, or a country which is exposed to a natural threat like an earthquake or a tsunami or any kind of other hazardous event, to anticipate, resist, absorb, adapt, and recover from these effects in a timely and effective manner. Okay, so if we're able to accomplish that, then we can say that we are actually a resilient system or person or community or country. And this is a very general definition that may apply if you look at one building, or at the whole network, or at the whole system of networks that are deployed over a geographic region. Okay, so if we take that to sort of a mathematical definition, we can basically look at two critical or two key functions. So on one hand, we have a system, which again may be a building or a network, that has a certain capacity. Okay, so this is the yellow curve. So before the event that occurs here at time 0, we have a certain capacity, okay? In an ideal scenario, this capacity is equal to the demand that a system has, okay? We know in practice that this is not always true. For example, the healthcare network is a very good example because usually the capacity is lower than the demand even before an earthquake, okay? But let's say that we have sort of an equilibrium here, but when the extreme event hits, we have, of course, a decrease in the capacity due to the physical and functional losses that may arise from this event. So if we prepare correctly, then we may have an equilibrium here, but after the event, we'll need to absorb a different catalog of losses. The demand at the same time, it may decrease or increase depending on the system we're talking about, but there will be inevitably some changes, and usually in most cases, the demand will sort of experience some decrease. But the decrease in capacity will be even more significant. So we have this difference here, which is what we understand as the loss, and we define the resilience in terms of the area between these two curves. So it would be this hatched area here. So the smaller the area, the larger the resilience of the system. Okay, so if we're able to experience low losses and recover slowly rapidly from those losses, then this area will be as small as possible. So if we take this definition, then in terms of if we aim to measure the resilience, then we need to measure as well as possible these two curves, the demand and the capacity. So how would this look if we want to look at the demand and capacity of a healthcare network? Okay, so this is a very simplified scheme, but we start with an earthquake scenario, which is represented in terms of a sleep model, which is how much displacement we can infer at the level of the tectonic plates. In this case, in the case of Chile, we have the Nazca and the continental plate that will suffer some kind of slip, and we can model that through different sort of geological and seismological methods. And we have some earthquake scenario that is characterized in terms of moment magnitude, an hypocenter that gives us the distance to where the networks are located, and this fault rupture model. So after that, we need to propagate this earthquake, okay, in order to understand how this sleep model is expressed in terms of actual ground motion at the locations of the different systems that we are interested in analyzing, okay? So for example, if we look at the regions here, this is just a schematic view, then we will have different networks, and we're interested in understanding which are the ground motions at a given location, and those ground motions are typically expressed in terms of peak ground accelerations and other spectral measurements that give us also a sense of the frequency content of the seismic wave and of the complete ground motion, okay? These ground motions are affecting a whole urban region that has, on one side, homes and different kinds of buildings where people are located, also buildings that host commercial and industrial activity, and also the buildings that make up this critical healthcare network, okay? So we will have hospital, primary attention facilities, and different kind of components of the network that are functioning in combination. So on one hand, given that we have a model of the urban environment and of the facilities that make up a healthcare network, and that we also know or can sort of estimate the ground motions, we're able to use different kind of structural analysis methods. So this is way outside of my expertise, but it's the expertise of my colleagues at CIGIDEN. So using different kinds of nonlinear analysis, we can predict the damage state of these buildings in very complete detail. And from that, also by analyzing the way that the systems work and how the different buildings and components of those buildings determine the way that patients flow across an hospital or a combination of hospitals, we can also understand the functional losses that are expected in terms of, for example, the attention rates and the attention capacity after the earthquake. Okay, so that's the capacity side. And then on the other hand, we also know that the overall built environment of the city is affected. We can also use fragility and vulnerability models to understand the performance of this sort of aggregated building stock in case of an earthquake, understand or predict the distribution of damage states and casualties, because these buildings are the home of people, and that will be affected by the debris, for example, and by the different structural effects that arise from structural depth. So with that, we can also model the demand and sort of match these two and understand which is the difference between these two quantities. And of course, this is sort of presented for a deterministic case for one scenario, but this is embedded in a probabilistic framework where we analyze these demands and capacities for a whole range of possible earthquake scenarios and sort of assign a probability to those estimations. So in this process, which is very complex and has a lot more detail, there are many components and several stages where artificial intelligence can help. Okay, so I'm going to talk first about how we are using artificial intelligence in combination with remote sensing imaging and also different data sets available in Chile to have a very detailed model of the urban exposure. Okay, so this sounds like a simple component on the model, but it's actually quite hard to model with accuracy and completeness. And we need not only to have a complete inventory of what is there, so not only to count buildings, but also to characterize them in terms of features that determine their performance to different hazards. So in the case, for example, of earthquakes, we need to know as well their material, their height, and their structural systems, and age, because with different combinations of those variables, we can also sort of infer the different structural taxonomies that they can be classified into, incorporating in this process a lot of knowledge of structural engineering, building codes, and sort of also the construction practices that are prevalent in each country. So this is where I have been working for a while at CIGIDEN, and also now with different approaches that I'm sort of learning at CENIA. And the first, there's a whole range of approaches here to sort of advance these exposure models. Okay, so the first approach on one extreme is fully data-driven. Okay, so we can resort to different data sources available at different countries. So in the case of Chile, we have, for example, public data sets provided by the Internal Revenue Service, this is SII, the census, etc., that sort of provide different pieces of the information that we need to build a complete exposure model. And also we are looking at developing exposure models that are scalable and that can be replicated at a national scale, and are not only available, for example, for Santiago, where we always have more data and more sort of information that can be incorporated. So we have done this several times, so we have quite a bit of experience in processing these data sets and also in dealing with their limitations. Okay, so every data set has a different purpose. For example, census data is aimed at understanding people's homes. So that data is expressed in terms of dwellings or homes and not in terms of buildings. And the same for tax cadastre data. It's defined in terms of properties that pay taxes and not in terms of individual buildings. That is what we're interested in inventorying. So there's a whole sort of very detailed process, data processing pipeline that we can implement to actually turn this data into an exposure model. But we are still aware that this data is not really complete. We are aware of several uncertainties and inaccuracies in the data, and every data set presents limitations that are then transferred across the risk and resilience estimation method. So while looking for alternatives, we have also looked into the completely opposite extreme, where we have a fully automated process to develop exposure models. So this is a collaboration that we have worked with colleagues from DLR, the German Aerospace Center. And what we have been trying to use here, what we have tested and sort of looked into different approaches for taking advantage of remote sensing data for exposure modeling. But one really interesting approach is to take advantage of street level imagery. So this is basically Google Street View, or for example, Mapillary, where you can obtain actual facade images of buildings. So the idea here is that if we think about which would be the most precise and complete ideal way to develop an exposure model, would be to have an engineer go walking around the city and look building by building and classify that building into a set of structural categories. Okay, so of course that's impossible, but we can sort of replicate that process or that idea using convolutional neural networks. So in this case, what we have is what we built is a set of facade images of many buildings in Santiago, and we use convolutional neural networks to do an automaticized classification of this building, of the buildings. There's a bit of that processing here, but because we do is extract around 200,000 images of buildings in the region of Santiago. We have to filter those images to extract only the images that are actually building facades. And then those images are sort of input to a supervised learning algorithm that outputs a structural taxonomy or structural class for each of those buildings. Okay? So the challenge here is that, of course, we have we can access a lot of images, but we have very few labeled images. So this is where the collaboration with engineering becomes really, really significant, and this is sort of an interdisciplinary problem, because we need sort of a hierarchical expert-based scheme to develop a labeled data set that can be used later for the training. So what was done here is to develop a hierarchical labeling methodology that uses the information that engineers can provide in terms of what kind of structural taxonomies you would expect for different kinds of buildings based on key variables, like, for example, building height. Okay, so, for example, in Chile, if a building is over 5 floors, then by defect, it should be a reinforced concrete building, okay, because the seismic code defines it that way. Okay, so there are several rules that can be applied in this labeling scheme, so that in the end we have sort of a one-on-one match between labeled images and these structural systems. Then that labeled datasets were used to train different convolutional neural network architectures. There were several experiments run here, so I'm not going to go into full detail of the architectures and the different experiments, but as an overall result, what we find is that give and take with different training schemes and training procedures and different architectures, we were able to reach around 80% accuracy in terms of building image classification. Okay, so this is a very promising methodology that, of course, we can continue improving and sort of deepening in order to obtain higher and higher accuracies. But we are in any way limited by the availability of the data. Okay, so this approach has some challenges. So of course, it has a significant computational cost. But also, more importantly, maybe this kind of street-level imagery is typically available at main cities like Santiago. But if you move out to the rest of the country, then this kind of data are not available. So we wouldn't, even if we had computational power, we wouldn't be able to apply this countrywide. And also, the labeling, of course, is very costly, and it's not straightforward to assume that the labeling that we have already established can easily expand to the rest of the country, because construction practices and stories vary across the country. So there are some sort of practical limitations, and we've been trying, given these limitations, to sort of advance towards a hybrid scheme where we can combine our knowledge on handling the data that we have available in Chile and that we know is consistent and constantly updated, or at least constantly published, and that is openly accessible, with some machine learning approaches to at least assess the inaccuracies in this data and gather and get a better understanding on where this data should be corrected in terms of completeness and accuracy, and also update. So, for example, one approach that we have been using is using drone-based imaging to automatically extract building footprints and heights. Okay, so as I have mentioned before, so one of the key inputs that we need to know about buildings in order to be able to classify them is their height. Okay, so there are several remote sensing data sets that provide object or surface height. So, for example, LiDAR data provides very detailed and very high resolution digital elevation models. Okay, there are also some digital elevation models that can be that have been generated, for example, from radar interferometry data globally. Okay, but these data are unfortunately not widely available or accessible for Chile. Okay, so LiDAR data, for example, is very scarce. There's an ongoing project actually at Scientifiques to sort of promote Chile in 3D, where we were trying to sort of get the interested parties to gather as much data as possible. And we can use those data to automatically detect footprints, measure their height, and then compare with what exposure models based only on data say, so that we can sort of estimate at least the uncertainties of the models that we have built based only on data, to correct them, update them, and sort of improve our modeling. What we would like to do now, and this is a sort of an initial collaboration also with colleagues at DLR, is to use this initial knowledge on high resolution elevation models that we can build from drone imaging, and in some cases also from LiDAR, existing LiDAR data sets, to train different artificial intelligence algorithms that allow us to build high-resolution normalized digital surface models from Sentinel-2 data. So this is multispectral satellite imagery with a 10 or 30 meter resolution, depending on the observing imaging, that is open access, and it's constantly available for the globe. And use input high-resolution models to train data sets that can be sort of generated for the whole country. So this has been tried already by them for tandem X normalized surface models. They have used, so tandem X data is a radar interferometry mission that has generated 12 meter surface 12-meter resolution surface models globally, but those data are not actually openly available for Chile. But they have been used to train Sentinel-2 imagery, which is available openly. And in order to train a deep neural network that can be used to estimate or to generate these high-resolution models based on Sentinel-2 imagery. So this is sort of our next step. We don't have tandem X data available, but we can try this same approach using high-resolution elevation models that we have generated previously and sort of retrain and or fine-tune the already existing data, so we can take our elevation models, sample them, obtain Sentinel-2 multispectral imagery at the same location and resolution, and then train different kinds of convolutional neural networks to generate different sort of estimated and synthetic elevation models based on ground truth and Sentinel data. Okay, thanks. So I'm going to stop there because I see that I'm running out of time. Thank you very much.
Thank you. And thank you for being on time, really. Questions? Okay, I have one. When you describe this resilience at the beginning, this difference between the two curves, so this is something that depends on time, of course. What if you consider blocks, physical blocks, that don't have the same resilience for the same kind of events, but that could correspond with each other? You know, you can have some links between the physical blocks, between the geographical blocks. So, I mean, is there any reason that a time and space model for this kind of modeling would make sense or not? Or is it already taken into account everywhere?
That is part of the question, actually, because we start by looking at independent networks. So, for example, we have, on one side, we have looked at the healthcare network. And on the other hand, we look, for example, we're looking at the electrical network. And of course, the recovery, so this sort of capacity curve of hospitals, depends as well on the capacity curve of electricity, because you have some sort of time where you can use emergency electricity, but then at some point you are depending on the network. So we're looking at those recovery curves in parallel, the same with water and with transportation. We still do not have the answer on how to combine them in one sort of integrated resilience.
And you think the dependency between the type of networks could be the same kind of dependency that we would have between Valparaiso and Santiago, for example, or between cities that are close to each other that receive the same earthquake?
Not necessarily, because I mean, on one hand, we have different settings. So, for example, healthcare networks in Santiago and the metropolitan region work very differently than in other regions with sort of a more rural setup. So the healthcare network is sort of different itself, and it has different properties, and the recovery and the capacity losses will be different. Okay, but on the other hand, Chile is very centralized. So kind of in the case of electricity and transportation networks, probably then the recovery and the capacity losses would be similar across the country. But in terms of healthcare, Santiago is very critical to the rest of the regions. So, for example, in case of an emergency or in case of an over-demand, patients in other regions would be transported to Santiago. And if Santiago is not working, then well, that impacts the rest of the country.
Okay.
But it's a very complex.
Yeah, sure. Thank you very much. Thank you again.
Thank you.
And now we welcome Rodrigo Carrasco, who is also in the same Institute for Mathematics and also director for data science in PUC. Maybe you will say that more than I do, but please, the floor is yours, Rodrigo.
Thank you very much, Antoine. Great. Thank you to the wizards at the back. Okay, so my name is Rodrigo Carrasco. I'm a professor here at Universidad Católica. I'm in a joint position with the engineering tool and the Institute of Mathematical Engineering and Computation. I'm going to be talking about this project we have currently as a Klimat am Sud project with Inria on seasonal forecasting of extreme temperature events. And I'll talk about the team and what we're doing and why somebody like me that I'm working in combinatorial optimization actually cares about this type of work. So the idea of the presentation is briefly give you a description of why we're interested in this type of problems, give a general overview of the project, what we're doing, and the team. We have a very interdisciplinary team, so it's a great team to work with because they have all these different expertises. And show one application in particular that I've worked with a student that came here to Chile to work from France in an internship as part of this project. And finally, the meat of the project would be actually the applications we're working in combinatorial optimization afterwards on how to use these predictions that I'm going to be showing you to actually make better decisions on different things. So, well, the effect of extreme weather, you can imagine, right? One of the typical things you can see, we saw this in Chile a couple of times already, the effect of extreme weather conditions, specifically temperature, has a lot of impact in different parts, has impact in agriculture, health, right? And all these different parts. You can see a couple of pictures we took back in 2017. We have this huge amount of fires in the south of Chile. Actually, you can see here, this was from an airplane, and you can see in the same place, 1, 2, 3, and I think there's another 4, 5 different fires at the same time just by the window of the airplane. So that was super, super complicated for our authorities to actually be able to handle all of those at the same time. So that's one of the things, but also not just high temperatures are terrible, low temperatures are also terrible. This is actually an example in Argentina where the effect of really cold weather made these towers fall. Basically what happened was extremely cold weather made condensation over the cables. They started adding layers of ice into it, and at some point the towers just didn't give up. And they just, as you can see, it's like just broke. There's a couple of videos online. I couldn't put them as a PDF, but you can, if you check it out, you can see there's a couple of videos on that you can actually see how the tower just collapses by itself without even, there's no snow at the moment. It's just the weight makes them collapse right there. So being able to, being able to predict these extreme weather conditions can help us. Specifically, for example, in the case of this type of problems, if you can, in the case of electricity companies, they can actually push a little bit of extra power into the cables so they're a little bit hotter and they don't have all that ice over them. So there's an easy way to prevent this type of things if you know beforehand that you're going to have this type of weather. So that's one of the key reasons we started thinking on how can we try to predict this type of extreme weather conditions with our team. Of course, despite the fact that they're extremely important, it's a really hard problem to do, right? We know how to predict averages, we know how to predict the weather tomorrow. We have a lot of tools in there, but try to predict seasonal, long-term extremes, it's a much harder problem. So we have a lot of information on the short term and on weather prediction, but these long-term things are more complicated. And the other thing is, in South America, it's even harder because we don't have data sets to do it, right? So the effects of El Niño, La Niña, and all the different things that affect the southern cone of America, they are really important here, and you don't have data to do it. So how can we actually do this? So one of the interesting things that happened a few years ago, there's a paper by Collarzo, a colleague that's working in this project. I'll talk about her in a few minutes. And she works on models on how to predict extreme weather conditions. So they're working in Argentina to see if they can come up with techniques that can predict the effects of, in this case, there was high temperatures in some parts of Argentina, and they show that they can actually have a very good prediction with some difficulties with the data that they were having. So then we started thinking, can we try to connect all these different ideas that they had with the things we're working in prescriptive analytics here in Chile, and create a team that can actually grab this problem somehow and try to say something smart about it. So the idea was to first jumpstart a multidisciplinary research group that mixes climatology, data science, probability, and statistical techniques, all together to try to see if we can come up with solutions for these type of problems. Explore the predictive capabilities of different techniques that we've been trying to use for doing this. Specifically, the team that's in France and Uruguay are doing this type of things. Combine this data with different data we're collecting with different machine learning approaches to try to develop new tools that can actually help us do this type of predictions. And the important thing that we're working here in Chile is explore how can we use those predictions to design things better or to make better decisions on how things are working. So that's the key what we're doing here in Chile. So the team, as I said, it's a multidisciplinary team. In Uruguay, the person that's actually running the whole suit project is Pablo Rodriguez. He's from UDELAR and works mostly in predictive modeling and data and network data analysis. But in his team is also having Madeleine Renom. She works in atmospheric science, and Diego, who's working in applied machine learning. So that's the team that we have in Uruguay. In Argentina, we have our climate team, right? Matilde Rusticucci, Mariana Burragan, and Soledad Collarzo. All of the three of them work in climatology. So they've been working for a long time, and they're very well known for their models on climate. So they're helping us try to understand how we can grab that information and try to use it to make something smarter. In France, we have a big team as well over there. Yassine is leading the project from the France side. Gerardo Rubino, who works a lot in machine learning, he's the one that's also doing a lot of things in that area with us. And Sebastian is the one that's doing the computations on neural networks. And here in Chile, I'm the one that's doing the coordination of the team. We have a bigger team with Javiera that works in applied probability, and Eduardo Moreno, who also works in combinatorial optimization. So as you can see, it's a team that's very diverse. So we have people that know about climate science. We have people that work on data science and machine learning. And we have a bunch of people, the three of us, that work on optimization. And I'm going to show you why we care about this. So let me start with the work that actually we did with Martin. Martin Richard, he's a student from Mercer. He came here as an exchange student, and he wanted to work on projects on climate change and see if we can do things. The interesting thing is, with this collaboration we have with Argentina and Uruguay, we already have a database of more than 100 different stations that we have in Chile, Uruguay, Argentina, and Paraguay. And we have data there for temperature, we have data on humidity, precipitation, and a bunch of different things. And the idea was, can we try to build some sort of technique that can help us grab that data, ensure that we're looking into the geographic connections of the different things, and try to see if we can actually predict if there's going to be an extreme event in the next few days, for example. So that's the idea of what Martin wanted to do. And the other constraint we added into the project was making sure that we can do something we don't need a supercomputer to do it. We need something that's easy, fast to do it, in case we wanted to do this maybe in a vineyard or something like that, as I'm going to show afterwards. They want to just have some sort of alarm that can tell them, in the next couple of days, we're going to have this type of event. The problem, of course, with weather is extremely, extremely chaotic. There's actually some simulations that came from a paper that Martin had to redo them to see what happens. And you can see the effect. These are weather equations, and you can see very small differences make completely different patterns in the short term. So the problem with this is trying to predict things in the long term. When you have this type of chaotic behavior, it's really, really hard. The interesting thing is people have been working using neural networks to actually do this. And in particular, one approach we've seen a couple of times being used is reservoir computing, where you have a big bunch of a network of neurons that it's trying to collect the effects and connections that you can see with the data. That's how I interpret the fact that you have this reservoir. And that reservoir is trying to help you find the patterns that you have in the back of the data to see if you can actually connect these things. And actually, this paper from 2020, they showed actually that they can actually use one type of reservoir computing networks, in particular eco-state networks, to actually model extremely chaotic systems, and they can actually predict them really, really well by using this type of networks. So that's what one of the ideas we had with Martin was, let's try to see if we can actually use this to do something similar and try to predict the temperature of this chaotic system. We also have been trying with another former student of mine and a colleague, Gonzalo Ruz. We actually been using ecostate networks a lot for doing predictions in other settings. We've been working a lot with the ALMA radio telescope, and many of the the fault detection systems that they have running up there, we created them with this type of neural networks. So we thought, since they work really well with highly noisy data and they work really well with chaotic systems, let's try to connect the two and see if we can actually do it. And also the other thing is, ecostate networks, they are really good at being able to be trained with a really low amount of effort. So you can train these systems with not a lot of time compared to other typical techniques you use for this type of things like LSTM and TACNs, okay? So that's what Martin embarked in, and he started working on see if he can actually create this sort of thing. It was a lot of try and error because it's a really hard problem to try to tackle. So Martin tried different configurations, different types of networks, and see if he can actually connect these things. The first thing we found out is, although you can grab part of the prediction, it's really hard to do it, and the ecosystem network by itself is not enough to actually do a good prediction on this. We have a lot of data, as I said before, we have all these 100 stations, we have data from the 1950s, so we use all that data to try to train and separate it as a training and testing set to see if actually this is working. And even if when we used large ecosystem networks, they weren't able to grab the data from just one weather station, it wasn't good enough for doing the predictions. But once we started grabbing a whole region of, as you can imagine, when you grab a whole region, then somehow the network starts learning part of the connections between the geographical locations inside this data, and it performs slightly better, not very good, but slightly better. So we kept on looking on how to improve this, and we came up with boosting algorithms. So by the end, we used boosting algorithms to try to connect all these different predictions we have from the ecosystem networks and actually do a better prediction on what's going to be the extreme temperature we're going to have in the next 3-4 days. And actually, this actually worked really well. We used XGBoost to do the prediction. We also used transformers and different things, but the one that performed the best was boosting. And as you can see, we use different approaches, just using the maximum temperature and minimum temperature, and also using networks, a network of who are the closest neighbors to each of the different stations. Using all that information, you can see we can predict with a small error, around 3 degrees, the extreme temperature of the next 3 days. So okay, that was an interesting result we started getting with Martin, but why do we care about this? That was the question, since we're working in combinatorial optimization, why do we care about this type of predictions? And the idea here was try to use that predictions to do better in terms of decisions. And in particular, the team of Eduardo and Javiera, they've been working a lot in network design. The same project I showed you before, when you have this collapse of towers, right? That is, Paula helped me with all the explanation of resilience, right? And the thing is, one way of looking at networks and see the resilience is what happens when you have faults in them. And what Javiera and Eduardo have been working a lot is what happens when you have correlated faults in them. And the thing you can see there is that even if you're using optimization models to try to see what's the best way of expanding a network, for example, if you don't take into account the effects that you have of correlated faults, then it's really bad decision. And basically what they've been creating is new techniques where you can do a design that is resilient in terms of correlated faults. So now that we have these predictions where, what is going to happen if there's going to be something that's going to affect a long area of Chile, for example, now you can have a better handle on what type of scenarios you want to use in your model. So that's one of the ideas we wanted to use. And the one I'm working in with a couple of colleagues is on the use of prediction of solar generation. One of the things you can have, if you have really cold weather or hot weather, that affects a lot the way your panels are producing energy, and also your storage, how good it's working. Yeah? And we're working for a couple of years in developing decision support tools that can help us manage when you have uncertain generation that you had with the sun, but also when you have storage. If you don't have any storage, of course, if you have more than you use, you just drop it. If you don't have enough, you'll have to buy it from the grid or just have a blackout. But if you have storage, then you can start hedging if you have different prices. And we showed that we actually built a couple of solar power plants, and we are running some stochastic optimization algorithms over them, and using that to show that using those type of techniques, we can actually do better decisions than what all inverters are doing right now when they do the energy management. So that this type of, the thing is, for actually being able to model these problems as a stochastic optimization problem, we actually need to create scenarios for them. And here's where we connect with the Climat project, where this type of scenarios help us, decide what type of things we should put as scenarios in the stochastic optimization problem. Because not only you can use data to create the scenarios, and you can see here, we actually created new techniques that can help you do the optimization and the prediction at the same time, using adaptive partition methods that help you decompose the stochastic optimization problem and at the same time create scenarios with this, and we can use that. But we need historical data anyway, and these type of techniques that we're getting from our colleagues in Uruguay and France can help us actually feed this stochastic optimization problems to make better decisions. So,
thank you.
There you go.
Thank you, Rodrigo. Thank you. So, first to comment, I'm very pleased to see the Climate Amsud program working. It's for those of you who don't know, it's something very new, which was created above the Mat Amsud and Stick Amsud programs that are very old. And I think we can thank again the embassy and all the programs to sustain that kind of very interesting work. So thank you again.
Thank you.
Questions? Yep, go ahead. Do we have a mic? Okay. I have one also.
So thank you for the talk. It was super nice. I have a semi-serious, not so serious question. Why would you use XGBoost and not, for instance, scikit-learn?
Compared to what? Instead of what?
Instead of scikit-learn.
Oh, actually, we actually use, when we use EcoSec networks, we actually use the Inria models for testing everything there, so we try that. And just trying different things, and that was the one that worked. It wasn't any specific reason. But the EcoSec network we actually tried out was with the one that's built in the Inria repository. So.
Okay, because the performance is more or less the same, depends on the data set, but we also have like this possibility to have a quantile regression using histogram gradient boosted trees. So I think it would be nice to have like an interval of confidence around the predictions.
In another project, we can talk afterwards, but in another project, we're doing the prediction for how long it takes ALMA to do the processing of their projects in the servers, and we're actually using that for doing the quantile regression and predicting the gaps and doing smarter scheduling with that. So we know that it exists, but Martin didn't, so I'm not going to blame him because I could have said anything, but yeah.
Excellent, thank you.
Thank you. No other questions? So I have one. I'm not an expert, but I've heard, in particular, I have someone in my team that works on that, on extreme theory, that, okay, it is difficult to model the extremes in time, but it's even worse if you consider time and space dependency and the asymptotic dependency of the maxima in space. So how do you handle this, given that, of course, you are interested in time extreme events located in several areas? How do you handle the space dependency?
Yeah, okay, so in our case, the specific project we work with Martin, we just were sort of lucky with the way we grab things by grabbing monitoring points that were close enough when we're training so we had several different networks that were working in close relationship with each other.
Okay.
But in the case of Paulo and Gerardo, I couldn't show because of time, I couldn't show all the work that they've been doing. They actually are using graph-based models that connect the things, and they
Okay.
also have the distances in there, and they're dealing with geographical locations in that way. So it's more sophisticated.
Okay.
But it's super hard to.
Yeah.
We thought it was going to be much easier. Maybe we're overconfident on when we try to tackle it. The climatologists, they were like, yeah, you surely can do it. I mean, we could do this, and we thought we could do it easier, but we've been working for a year and a half. It's a hard problem.
Okay, cool. Thank you. Thank you again.
Thank you.
Okay. Last but not least, as we say, so I think we have Guillaume from Lille. So the Spirals team. So Guillaume Fény is coming from France also, and from Inria, from the team Spirals in the northern center of Lille, where it is very cold right now. Go ahead.
Thank you very much. So hello everyone. So I'm a member of the Spiral team, where we work on a lot of energy things. So my work, I will present my work on the modeling of the power usage efficiency of computing infrastructures. So for a little bit of context, so energy is one of the biggest expense for data centers. There is a large amount of data center in the world, especially thanks to cloud computing. Their combined electricity use more than double in less than 5 years, and actually represent between 0.9 and 1.3 of the global electricity consumption. It is expected to attain at least 3% for in 10 years. So such infrastructure are operated by a large amount of software systems, especially for supervision, scheduling of the task, the networking and data storage. While the energy efficiency of infrastructure is extensively studied, there is a few studies on the energy impact of software on such infrastructures. So in order to analyze the energy efficiency of an infrastructure, you need to know the energy consumption of its components. But to estimate the energy consumption of its components, you need to measure or estimate the hardware and software energy consumption. And you also need to adapt to a heterogeneous environment, because such infrastructure feature a wide variety of hardware and software. So the goal of my research is to enable the end-to-end assessment of the energy efficiency of software deployed in such environment. So in our team, we have the Power API project, which is we began to be just a set of tools. It is now an industrial academic consortium with several members. So we have, of course, Inria, and Orange Labs, which is a French ISP, OVH Cloud, which is one of the biggest cloud provider in Europe and in France. We have also Davidson Consulting. Now the project is provide a green computing toolbox, so there is a lot of tools which are open source and available on GitHub to measure the energy efficiency of the infrastructure and of software. So the first work I will present is SmartWatt, which is a software-defined power meter for containers. So the goal of this contribution is to estimate the energy consumption of software containers and provide the estimation for the CPU and the memory. So in the literature, most of the power models use an offline calibration phase, which is tightly linked to the hardware. So you need to calibrate it for every hardware you have in your infrastructure. So it takes a lot of time to do that, a lot of energy, because you need to generate a data sample of the behavior of the machine using synthetic workloads or benchmarks. So we want to remove this step by learning the power model over the time with the natural activity and inactivity of the machine. And also the goal is to seamlessly support the heterogeneous infrastructures, especially where we have a lot of different hardware configuration, especially CPU models, for example. So in our case, software containers are the entire runtime environment of the application. So you have the application, its libraries, and other dependencies. It can take several forms, so you can be Docker containers, Kubernetes, systemd services, or virtual machines. And we mostly use them based on Linux control groups. So we use control groups to monitor the hardware performance counter for the running containers. The advantage of the counters is to provide information about the execution of the program on the hardware, especially the CPU. So you can have the amount of cycles or instruction or cache activity for the program on the hardware. They have a very low resource usage. You only pay the setup of the counter, not the running them. And they don't impact the application performance. There is a large amount of events that are available, but you can monitor everything at once. You have a limited amount of registers, so you need to carefully select the events you want to monitor. In our case, we use a correlation coefficient with the energy consumption coming from the hardware itself, because it can provide a global energy consumption. So the goal of the power models is to distribute the reference energy coming from the hardware across the running containers. So in our case, the power model that I learned online, we use the period of the machine activity and inactivity to get data sample, and the goal is to build a robust power model over the time. Under the hood is a multivariate linear regression, so the ElasticNet variant, because it is very efficient for this usage. It uses a very low amount of resources to learn the model and to predict with it. And it has a very good accuracy for our needs. So to deploy smartwatch in an environment is very simple. There are two main components, so the sensors that we deploy on every machine of your cluster, and you have the parameters that will take the data of the sensor and to provide the estimation. So I will present you two examples environment. So the first is the high performance computing one with a single powerful node where there is a NAS parallel benchmark running on it. And the second one is the cloud computing cluster, so Kubernetes cluster, where we will run a distributed data processing pipeline. So smartwatches allow you to estimate the energy consumption of the different targets on the machine in real time. So it allows you to get, for example, the kernel impact on the energy and the system services. And you have the workload. It can be run sequentially or in parallel, of course. You have another point of view with the cloud computing case, where there is a cluster Kubernetes composed of 6 nodes, where we deploy several application clusters inside. So we can use smartwatch to get an insight of the entire cluster for the different power consumption. So you have at the left the CPU share and the memory share of the consumption. So there is 90% of the energy of the infrastructure that goes into the CPU. At the middle, you have the different services. So you share by services. So the consumer consumes 65% of the entire energy, for example. And at the right, we have the different nodes. So the shares of the total energy going into the different nodes and infrastructure. So this allows to have a very a big view of the different consumption, different parts. So the concern is the power model accuracy of smartwatches. the model are learned when we exceed a specific threshold, so a user configure threshold from the CPU reference. So for example, for the CPU, this is 5 watts, for the memory 1 watt. And we can see that the mean error of the models of the machine are always below the set threshold. So this means that smartwatch is able to respect the constraint on the models. Concerning the resource impact on the system it deploys to, so each component of a smartwatch is a container, so it allows smartwatch to monitor itself. We can observe that the impact on the monitored system is very low. It is by design because we use the hardware performance counters that don't disturb the software execution. And the sensors that deploy in every machine consume very low energy, like we can see 0.3 watt on average. So smartwatch is a software power model parameter that can be deployed in heterogeneous environments, and it provides an overview of the infrastructure services energy consumption. So now that we have this overview of the energy for the services, we can talk about the power usage effectiveness of such services. So to do so, we propose XPUE. So this is an extension of the power usage effectiveness metric that is a standard, the most used metric by cloud provider, for example. And we extend it to provide an end-to-end view of the infrastructure energy efficiency, especially for the hardware and the software components. The goal is to highlight hotspot and inefficiencies on the infrastructure, to evaluate the energy optimization strategies, and also to spot and to avoid wasting resources, especially due to the oversizing of the infrastructure. So this is an overview of the existing metrics. So at the top, we have the water usage effectiveness, and we have the carbon usage effectiveness, and the power usage effectiveness. So these metrics are infrastructure-wide. So you have a very large grain of the measurements. And we proposed fine-grained metrics at the bottom for the server and the software platforms. So, like I said, the power usage effectiveness is a standard metric for measuring infrastructure-wide energy efficiency. Many data center operators communicate about it. So the worldwide average is 1.69, but it's far lower for data center operators, especially for cloud computing ones. For example, OVH Cloud have an average of 1.28, and for the data center of the Google Cloud Platform, it average of 1.10. So it is defined as such. This is a ratio between the sum of the energy of the entire data center on the sum of the energy of the IT, which is a part that contain, for example, the cooling system and other network equipment, etc., that running the infrastructure. So we propose to use the same for evaluating the server power usage effectiveness. So it will be composed of the machine power consumption coming from the power supply, for example, with connected to a power meter or PDU or IPMI, and the consumption of the computing hardware, especially CPU, GPU, FPGA. So this is the same as the PUE. And then we need to evaluate the energy efficiency of applications. So to do so, we use the energy consumption of the computing hardware that it runs on, and the energy consumption of the software services running on the machine. It is based on the smartwatch, the parameters that I presented previously. So when we have the different ratio of efficiency for the different part of the infrastructure, software and hardware, we define the cloud power usage effectiveness, CPUE, which evaluates the energy efficiency of cloud infrastructure. This is a combination of the SPUE and VPUE. and it allows to support a multi-level software architecture. For example, a Kubernetes cluster deployed in a virtual machine of an OpenStack cluster. So the number of levels depends on your platform. So for example, Kubernetes, this is just a product of the SPUE of the machine that we run the cluster on, and the VPUE of the platform itself. So I will give you a little some examples of the metrics in action on different hardware configurations. So we have Intel and AMD CPUs with machine hosted on a Grid 5000, which is a French test bed for experiments. This is the classical machine. In this case, a Dell machine, to be precise, with air cooling. And we have machines hosted by OVH Cloud, which is a cloud provider. And they use more optimized machine and water cooling for their systems. So for the first showcase of the SPUE that shows the efficiency of the hardware itself of the machine, we can see that a machine in blue hosted by OVH Cloud, so an AMD machine, and this equivalent in configuration in red on a Grid 5000, we see that there is a significant difference of efficiency for exactly the same hardware. We are open for the SPUE for the OVH Cloud machine, and 1.7 for the Grid 5001. So this shows that the optimizing your machine is interesting at the scale of an infrastructure. And another example, you have the yellow one on Grid 5000 that was have one Intel CPU, and you can have the equivalent on OVH Cloud with 2 Intel CPU, and we have very close SPUE, but you have double of the resources. So instead of having, for example, multiple machines, you can stack your workload on one bigger one and have a better efficiency than multiple one. So concerning the VPUE, this is in real time for a Kubernetes platform. So at the top, you have the power usage in real time for the containers that go into the containers. And the second one is the Kubernetes services. And you have the VPUE computed in real time for the entire infrastructure. So we can see that at the beginning and at the end, when the infrastructure workload is at its lowest, you see that the VPUE increase, which is normal, because the infrastructure is doing practically nothing, just running itself. So this shows that in order, of course, to have a lower VPUE and so an higher energy efficiency on infrastructure, you need to run things on it. Another point of view for this, you have the VPUE Kubernetes by the amount of worker on the infrastructure. So for one worker, you have 85% of the total energy that going into the containers, so the workload, and 14% that goes into the services. As the more you add workers in your infrastructure, you see that the part of the service is reduced, and there are more energy that goes to your workload. So it also shows that if you have such a distributed infrastructure, you need to take profit from it and not let it at rest doing nothing. You have the same behavior on OpenStack infrastructure, but by design, OpenStack have a lot more services to run itself. So the share of infrastructure services for one worker node is even bigger, 24% it used just for it, and 75% go into the VMs. So we get the same behavior when we add worker to the infrastructure. So now for the CPUE of the platform on specific hardware, this shows that the different platforms, so the row and the hardware configuration on the columns, you see that we can back the OVH Cloud AMD machine, which was the most efficient one for the SPUE, And when you deploy a platform on it, you get the most efficient configuration, and the worst one, you can see that it adds pretty quickly. And when you stack the different configuration, for example, Kubernetes on an OpenStack cluster, you see that it increases even further. So you saw that this stacking the infrastructure have a very great impact on the efficiency. Now we have the same behavior on the different platforms deployed in different locations. So for this case, we have the Grid 5000, which is our reference, and OVH Cloud deployed in different infrastructure around the world. So for some reasons, sometimes you have the infrastructures that are less efficient. So for example, Singapore and Sydney. So you see that deploying the different infrastructure have a far higher GPU than deploying it on, for example, efficient location like Gravelines in France or Beauharnois in Canada. And another application of the indicator in the platform on the location, but in carbon usage efficiency. So the unit is a gram of CO2 per kilowatt hour. So the two locations that are the most efficient are Beauharnois in Canada because their energy are coming from hydroelectricity, and OVH Cloud Gravelines is coming from nuclear power, so this emits a lot less CO2. And the counterexample, like Singapore and Sydney, that use a lot of fossil energy, you can see that you generate a lot more CO2 for exactly the same workload. So this shows that the location is also very important if you want to be efficient. So I presented you the different energy metrics from end-to-end to the infrastructure. So I showed that showing efficient hardware is very important because this is it added up pretty quickly. It is better to maximize your infrastructure use and better to avoid the staking software layer, especially virtualization. This is something really done often, unfortunately. So to conclude, I presented you my two contributions, so SmartWatts and the XPUE. So everything is available on the Power API website. If you are interested or have further question, you can send a mail on this alias, and we will gladly respond to your question. So thank you very much for your attention.
Thank you, Guillaume. We have time for one question or two. Okay. I have one. You mentioned the difference of efficiency between Google and OVH. So it was 1.1 for Google, 128 something.
Yes.
So what makes such a huge difference? Because I guess this implies lots of euros of consumption, etc. So what is?
This is mainly the concept. Well, the multi-part, but mainly the consumption and the location, because Google Cloud Platform have a lot of data centers in countries that have a cooler temperature over the year. So of course they use a lot less cooling, and this is mainly what shows this difference. And there are sometimes for the mean global mean is 1.59. Because most of the data centers are not really huge, and they use AC, classical AC. So this it's not possible to see half of their energy usage going into the cooling of the infrastructure. So this is mainly the difference. This is what they do to improve their efficiency.
Okay, and I have a last question. Are there any works that forecast the evolution of these numbers that you gave, thanks to, well, because of the climate change and the increase of temperature? Because, as you mentioned, it changes things a lot. So, are there measures? For example, Luis showed that 2023 was a very hot year. So, did they see anything changing, and do they forecast anything in the future due to the global warming?
To be honest, these numbers are mostly coming from the cloud computing. They removed the part of the cryptocurrency mining, because otherwise we have at least more than 4% of the global energy usage for the data center. But yes, this is mainly.
Okay. Okay, thank you very much. Another question, sorry. Thank you, Luis.
No, first a comment and then a question. You were mentioning the importance of these Climate and Sud programs, and we have a Climate and Sud project with the spiral teams and universities in Uruguay and Paraguay, and also we have now an associated team with the spiral teams on this. The first one is called Green AI, where we are applying these principles to let's say, to the AI domain for controlling the energy consumption of AI. And we have this also associated team called SUSAIN, on Sustainable Artificial Intelligence, on the same topic. So it's very interesting and it's very nice to see this happening. I have a question that is more practical. It's like, what is the, let's say, human effort of using both of these software? What do I need to do to start measuring the energy consumption of my code, for example?
That was my last question also.
Okay. Mainly it depends on how deep you want your analysis to be. Because if you just want the consumption of the software or running on the infrastructure, it's quite easy actually to get the tools working. But when you want to go deeper into the infrastructure, well, you are dependent of the actual data that can be recovered on the infrastructure, and this is mostly the pain point, because sometimes in the infrastructure they don't even have very detailed conception of the services or the, for example, the network equipment. This is mostly the biggest problem every time. So this is just an aggregate, a global aggregate. You can't really do anything with it, unfortunately. But yes, it mostly depends on what the infrastructure is able to do.
Thank you. I want to thank all the speakers again for this afternoon. Thank you very much. Thank you. Thank you very much for being exactly on time, because we started 10 minutes after the time, and it's just 10 minutes after. So congratulations to all of you, and thank you.
Thank you very much, Antoine, and all the speakers of this session. And now we will welcome Cécile Vigouroux from Direction of International Relations at Inria, who will tell us about the Franco-Chilean cooperation programs.
Thank you, and thank you for giving me the opportunity to say a few words, but the presentation will be made by Claire Saint-Léger later on, together with Luis Martí, since this presentation will be divided into two parts. First of all, the Inria French-Chilean Network for Researchers, and then a focus on cooperation programs. So I just wanted to say, first of all, that I thank the organizing committee for putting up such a nice event. This is only the first day, but we are going to have 4 very rich and fruitful days in different universities. And we wanted to do a focus on the cooperation programs to emphasize the fact that Inria is really putting a lot of effort to support this collaboration, because it is a strategic collaboration for the Institute. And this collaboration has been ongoing for more than 10 years now in an institutional level, but of course there were already a lot of collaboration beforehand. And now we are opening a new step in the cooperation. As it was mentioned this morning, there are a lot of discussions with the Ministry of Science and Technology here in Chile, and that's why we want to really underline the importance of the network, because there have been a lot of researchers. I think it's more than 650, both on the Chilean side and the French side, that have been working together. Oops, here it is. Thank you, Nayat. And then, as you can see on this slide, a lot of collaboration already ongoing. We can still, of course, develop more things, and in order to do so, you have the classical tools that can be used, that are developed by the embassy, for example, but also some tools homemade, so to speak, by Inria. And therefore, I leave the floor to Claire and or Luis to present the network and the cooperation tools. Thank you.
Thank you, Cécile. So I am Claire Saint-Léger. I'm working at Inria in France in the International Relations Department, and I'm working with Inria Chile team to develop this network we would like to present. Luis, if you want to.
Well, we already met before.
So we have launched this network officially in 2022 during the first edition of the Scientific Days, which were online for the first time. But it was launched officially, but it fostered activities already led by Inria Chile team and the International Relations Department. But it was launched officially to make more visible the role of Inria Chile, to support the existing collaboration and foster new ones. And as the activities, Inria Chile, conjointly with our department, identifies the new opportunities in Chile and France, and the topics of common interest between our countries, and also identifies the research partner, which can be an interest for Inria teams, and on the other side, the Chilean teams, which can be of interest, which can be of interest for Inria teams. So we are doing some scientific matchmaking if you are searching for partners in Chile or in France, if you are searching for postdoctoral students, PhD students. And another activity is networking activities. We in Chile organize scientific events like today, these Scientific Days. And we share information about this opportunity, the existing project and the funding programs, individually to some targeted teams, or also more broadly on Inria Chile website and Inria Chile social media. So concretely, there are some events, Journées Scientifiques, summer schools, local workshops, and we'd like today to have a focus on Inria programs and also on other programs with external funding to support your Franco-Chilean collaborations. So the first one, we've heard about several examples today. We've heard about Antoine Rousseau associate team with POOC, also the associate team of Frédéric Semet team Inox. And so this is an Inria-made program to fund bilateral projects between Inria team and a research team abroad, in this case Chilean team, for a period of 3 years. And it funds visits and workshops. With Chile, the program is really successful. Since 2012, we had 30 associate teams, and nowadays there are 8 associate teams, among them 4 with the Pontificia Universidad de Chile. Another program, good opportunity. Nowadays we don't have any beneficiary, Chilean beneficiary for this program, so this is a call to Chilean researcher, but also if French researcher identifies collaborators to be interested in this program. It's named Inria Internal Shares Program, and it allows Chilean researcher, for example, to spend a few research stays in Inria Center in a team identified. And there are 2 tracks. Track which exists since years, which called Advanced Inria International Chairs, dedicated for permanent researcher, more senior. They can spend between 10 and 12 months spread over 5 years at Inria, and they are paid during these stays. The idea is not to realize the period in once, it's to have several stays during the 5 years. And we have created quite recently, like last year, another track for more junior researcher. You can spend 6 to 9 months over 3 years at Inria. Another program is that we dedicate some Inria postdoc position to international cooperation. Each year we have a number of slots reserved to support international collaboration. The postdoctoral fellows as recruited by an Inria center, but I encourage to visit to the partner abroad. And today we have 2 ongoing postdocs working on projects with Chile. This is an annual call also launching in June. And of course, we've heard about this program this morning also during the introductory call and also during the presentation. We have a successful internship program led by Inria Chile in partnership with 3 Chilean universities, among them the Pontificia Universidad de Chile. And each year we have up to 5 students for the book who spend 3 months internship in an Inria team, which allows to reinforce the links between the French team and the Chilean team, and also leads sometimes to a continuous collaboration with another project. We can see an associate team thanks to first contact as an intern. There are several examples successful. And there are also the Inria program we would like to focus on, but there are also another program outside Inria, which is supported by ANID, the Chilean National Agency for Research, and for France it's supported by the Ministry for Foreign Affairs and the Ministry for Research, and it confounds bilateral projects between Chilean and French teams with an annual call with a deadline usually in May. So some of you may have benefited of this program. It's really useful also to support your collaboration. And the last program we'd like to present, to highlight today, is a regional one. We had also an example presented by Roberto Carrasco a few minutes ago. It's a program supported by ANID from Chile, and from France it's supported by the Ministry for Foreign Affairs, and it involves several institutes, CNRS, CRD, Inria, CIRAD, and EMT also for the STIC part. There are 3 thematics: mathematics, digital science, and climate. It funds a 2 years project which involves at least 1 French team and at least 2 South American teams from 2 South American countries. And it funds also research mobilities. So there was the program. If you have questions to find the right tools to support your collaboration, do not hesitate to contact Inria Chile team. They know very well the program, and for Inria program also we can help from the Department for International Relations, me and my colleagues. And more generally about the network, this network aims to support your collaboration, to create new one. We have presented some action, but if you have some ideas to develop these networks, Luis and me are very open to suggestion. I don't know if you want to meet more regularly by visio, or if you have another idea, do not hesitate to contact us or to speak to us in these few days. Thank you for your attention. It was a long day. If you have questions, we can answer.
Thank you very, very much. Please don't leave your seats. I have some final words, but then I have an instruction that you need to follow. It's not a game, but could be. So thank you very much to the director, the direction of the International Relationships at Inria for the presentation of the Franco-Chilean programs. We hope you can make the most of it by enlarging the network through these finding instruments. Thank you also to the authorities and to all the participants who brought life to this first day of the Journées. We remind you that tomorrow we will meet again, started at 9 a.m. and the Tigny Auditorium, Faculty of Physical and Mathematical Sciences of the Universidad de Chile, where we will have another exciting day filled with essential scientific conversations. See you tomorrow. Thank you very much and have a good evening. And now is the instruction. So everyone stand up. Give applause to you. And come to the stage. We are going to take a picture of all the people that have stayed with us until this very last moment. You deserve a prize. So thank you so, so much. Please approach to the stage. Each and every one of the people who is in this room. I'm not going to leave anyone to leave this room without being in the picture. Don't be shy. After a really long day, we're all very good friends. So just approach. Okay. Closer. Don't be shy. Thank you very much. See you. Oh. José, una desordenada, por favor. Like having really good fun. I mean, like you just had 2 pisco sours and some champagne.
Voilà, bah ça.